The following message is best viewed on an oscilloscope.
Okay, welcome, good morning. That's the usual intro we are now getting used to, very cool. So welcome to the dark matter session, the third one of this iChap. I just tell you the general rules and then we start in 2 minutes with the first presentation. So we have 9 talks in total, 20-minute talks, 5-minute discussion each. We will annotate the last 2 minutes on your slide. So you will see 2 minutes left on your slide in one of the corners. And if you really want to talk longer than 20 minutes, we will unmute and at some point stop you, of course. Everything is recorded. You can see this. It is also live streamed via YouTube. The attendance on YouTube is usually much higher than on Zoom here. We have a MetaMost channel. If you have any questions there, you can also write us there. You can also use the chat here. In the coffee breaks, we will stop recording and you can get a coffee and we just resume on time. And after the session, so after the nine talks, some speakers have their private Zoom rooms set up and they are linked on their respective Indico contributions. So if you want to discuss further and there is a Zoom link, please just join the speakers there. The rule is Katerina and I will have the camera on. The speaker will have the camera on. Everyone else has the camera off and is muted. And if you have a question after the talk, just raise your hand. Or if you're a co-host, you can just speak. And now I give the mic to Alex. He's the first speaker and he will report on the xenon wonton experiment. Please, Alex.
Great, thank you. I'll share my screen. Just need to close that. And share. Can you see it? All right.
Can you go to full screen? Yes, very good. I can see it.
Okay, great. So yeah, thank you for the introduction. Yeah, as was mentioned, I'm going to try and talk a bit about our xenon wonton experiment and the latest results, including the ones that we published quite recently, and give you a small glimpse into what are we currently working towards XENONnT as well. So for those that are not familiar with the xenon collaboration, we're about 170 scientists from all around the globe from 26 institutions, 11 countries. And this is just a small picture of part of our collaboration that well, attended the technical meeting that we had via Zoom a couple of months ago in May. Yeah. And this is how our baby actually looks like. This is basically the xenon wonton detector, which operated between 2016 and 2018 in the Laboratorio Nazionale del Cansasso in Italy. And the entire setup, the entire compound is actually situated underneath a mountain, quite a big one, which gives us basically something like 1,500 meters of rock overburden above our detector. So this entire complex is situated underground. And the detector is consistent of several parts. Well, as you see here on the left, is basically a water tank filled with 700 tons of pure water, and Buon Vito PMT setup that is basically on the inner parts of our water tank, as you can see this humongous picture. And also several calibration systems that allow us basically to have external calibrations, starting from a Newton generator for our detector. And here in the middle, we actually have our cryostat and the TPC, the time projection chamber, here in the middle. It's like basically a Russian Matryoshka doll. On the right, we have our 3-story cubicle setup underground. Basically, in the first, we have our xenon storage and recovery facility with some distillation column for krypton and radon removal. Second floor is the Q and slow control. And third one, finally, is cryogenic purification and some internal calibration injection points for krypton and radium 220. And this is how xenon wonton looked like, the actual TPC. It was rather smallish, although the biggest of its kind, but still small compared to what I'm going to show you later. It was 1 meter in width approximately and 1 in height, and had 2 photomultiplier arrays in total amounting to 248 PNTs with 2 tons of liquid xenon in target. And how this entire setup operates is actually quite simple, and this is the remarkable part of this entire technology for people that are less familiar with it. It's basically on this dual-phase time projection chamber concept. So we have our 2 photomultiplier arrays here on the top and bottom, and we have our xenon inside the TPC. We have our liquid xenon phase and a gaseous xenon phase. And if a particle comes and interacts, it produces scintillation light that can be detected by either one of those photomultiplier arrays, and also electrons. We drift those electrons upwards via electric field, extract them through the gaseous phase with another electric field, producing another scintillation light, proportional scintillation light, which can be again detected by either one of those photomultiplier arrays. And for instance, that allows us to know a lot about the actual interaction that happens. So for instance, the time difference between those 2 signals, basically this time difference, allows us to reconstruct the Z position of the interaction. The hit pattern on those photomultipliers gives us basically the XY position, whereas the areas of those signals give us the energy. And well, the most important part for this talk is that we can also discriminate between electron recoils and nuclear recoils using these 2 types of signal, basically the ratio between them. That's what you see here on the right bottom. It's because the electron recoils, for instance, betas on top, and nuclear recoils, hopefully WIMPs at some point, are on the bottom. And this remarkable discrimination parameter space allowed us to get some of the best results possible in this kind of well, direct detection experiments. So our main analysis result that you see here, where we unfortunately looked in the nuclear recoil band, it's colored here in red, it's 2 sigma, the lower 2 sigma part. We looked for WIMPs, we didn't find any. However, we placed the best limits on dark matter nucleus scattering, basically what you see here. We also had a different search, basically using only this 2 part of the signal and also placing some of the best limits on nuclear recoil scattering. And we can also use this detector to probe other more exotic effects, such as the Migdal effect, where we again placed the best limit on the planet on this interaction, or WIMP pion interactions, and so on. Besides looking at the nuclear recoil, which is quite interesting for WIMP analysis, we can however look also into the electron recoil band, which is situated here, and colored here in green. And we did this basically looking into dark matter electron scattering in this light dark matter paper that I mentioned just a second ago. And we again placed some extremely competitive limits, basically on lower energy dark matter masses. We also had this Nature paper where we looked exactly in the same band and discovered an extremely rare decay process, basically 2 neutrino double electron capture with a half-life of, I think, 10 to 22 years or so, basically a half-life that exceeds the age of our universe significantly. And well, if we have this data, we can also look into something else. Sorry, we can also look into something else. Well, if we have a data, we can make a background model, as we did for this, for instance, the 2 neutrino double electron capture, and it would look something like this. It's a bit overwhelming. There's too many colors. So for the point of this talk, the main part is to concentrate basically on the black dots, which is our electron recoil data. The red one is basically the overall background fit, and the main contribution to this overall background fit, which is led to HAR14. It's one of our most, the biggest contributors from radium to HAR22 chain in this region. And as you see, even from this plot, well, the actual agreement between the Monte Carlo data is quite good in the entire region between 1 keV to 110 keV or so. However, in the energy between 1 keV and 30 keV, we managed to achieve something that such detectors never achieved before, basically extremely low electron recoil rate of 76 events per ton per year compared to keV. And that allowed us to look for essentially excesses, which we did, and we found one. And this actually was and it still is quite a big topic, I guess, in our community. And not only journalists got interested in that, but there's quite a lot of publications still going on, and at some point there were like a dozen or so produced every day trying to explain this excess that you see here in this gray box. So what we observed was basically an excess between 1 and 7 keV at low electron recall energy region, with a naive expectation that we have 232 events, plus or minus 15, and the observed one is 285. And for the rest of my talk, I'll try and go through some of the things that we considered and we're still considering as an explanation for the success. I can't go through all of them due to constraints of times, but I think some of them might be interesting for the people that attend here. So one of the first things that we considered, and we ourselves and other people actually started pointing out, is, for instance, well, maybe it's just some kind of a binning effect. Well, like there's an excess here, there's an excess here, so there's probably an excess here as well. So not really. And this, first of all, we don't really do a bin analysis. We do one bin profile likelihood analysis. However, if you also consider, like if you concentrate on this plot, this is the bin which you see here on the right. And what we did here was basically to have this energy range between 1 and 30 keV, bin in 1 keV bins, as in this plot that we used. Again, I want to stress that these plots are used only for illustration. We don't actually derive any likelihood or anything like that from those. And basically what you see is that if we shift the energy scale from 1 to 30 keV to 1.5 to 30.5 keV while keeping the 1 keV binning, well, the significance of these supposed deficit actually fluctuates quite significantly between 1.5 to 3.4 sigma local significance, while the max global significance is 2.3 sigma, whereas the excess part really persists. Basically, it just, in other words, there is no statistically significant meaning to this point or this point here, which is basically just the others. We can also illustrate it a bit there while considering also our energy resolution. So what we can do is we can fit a kernel density estimation method to these data points in black, and that's what you see here as this black line, where the kernel width is basically into our resolution. So, and we can actually have this green and yellow bands from drawing Monte Carlos from the background model. As you can see here, if you actually even consider the energy resolution in this case, well, the local significance and global significance of this excess region is quite high, whereas these regions of supposed deficit and excess are actually extremely low. Basically, don't even reach 1 sigma global significance. So we can actually quite easily discard these statistical flaws as an explanation. So someone else can say, well, maybe you mismodeled your background. Well, for that, we check our background model with gradient calibration data. It led to 112 beta decays, which we use to calibrate our electron recall band. And this is what you see here, basically, in those blue dots. And there's going to be another plot that showcases it quite well later. And we see a good match between Monte Carlo and data, even up to low energy thresholds. It's also not a threshold effect because, well, our threshold is around 1 keV, whereas the excessive majority of it is 2 and 3 keV, where basically the efficiency is still extremely high. And we also try to double our threshold, and the excess still persists. And we try to do other profile likelihood analysis that PandaX still persists. So maybe we didn't mismodel on background, but we just slightly mismodeled the shape. And it is actually possible because I'm not an expert in this, but as far as I know, the beta decay spectrum, which is the most biggest contributing part to this thing on led to hard 14, is very hard to model at lower energies. And there is a bit of uncertainty on actual shape at lower energies, and maximum 6% of uncertainty, as was determined by an expert on such decays, which is actually done a dedicated study for us. However, to account for such an excess, we need more than 50% of uncertainty on that shape. So we can discard that as well. But sorry. So could it have been some kind of an instrumental background? So two of the main backgrounds that we consider in this kind of analysis, especially these energies, are AC. accidental coincidences, and surface background. So accidental coincidence, as the name says, basically randomness 2, randomness 1 paired together to create generating an event. And that's what you can see here in this yellow band. And the surface background is basically events that happen on the surface of our detector walls, which lose some of its 2 charge, and then they are basically getting lower in this 2 area and obviously in energy as well. However, both of them lie extremely far from not only the ER band, which you see here, but also the excess region still between 1 and 7 keV. And here in the Viridis 3D plot in the background, you see our rating calibration that I mentioned previously with the lead to 112 decay, which kind of quite well accentuates our basically electron recall band at which our excess lies. So could have we missed some background? And one suggestion that was suggested by colleagues and internally as well is argon contamination in our detector. And if we have some kind of an argon leak in our detector, basically air leak, which induces argon, we can have an excess of similar magnitudes and single quantities. However, in order to account based on preliminary estimations, in order to account for such an excess just from argon contamination, we would need to have a rate of something like several liters per day of an air leak. Whereas based on our GMS measurements and basically the purity of our detector declaration throughout Science 1, which we're using for this analysis, the rate of air leaks in worst case scenario would be lower than 1 liter per year. An additional caveat with argon is basically that it produces a monoenergetic peak at 2.8 keV, whereas the best monoenergetic peak that we can fit to this excess is slightly lower at 2.3 keV. However, we're still debating this also internally, and there are quite a number of studies still trying to understand whether this background can contribute in some additional way, or maybe there is some kind of additional contamination source that we still haven't considered. So it's not, if it's not argon, maybe it's a different kind of background. So maybe it's tritium, and this is something new that people recently enlisted in our field started thinking about. If we fit tritium to our excess that you see here, their actual significance is quite high, 3.2. And tritium has a long half-life, 12.3 years, and can be introduced to our detector in various means, for instance, just from its atmospheric abundance or basically through cosmogenic activation. And first, for cosmogenic activation, xenon, fortunately, we don't have any measurements to measure that. However, we could estimate and basically track the path of our xenon from above ground, where it can be actually activated, to underground, and eventually up until our purification point, because this tritium would be removed by our gas purification system. And the best estimate that we could achieve was basically to have something in the ballpark of 10 to minus 27 tritium ratio to xenon mole per mole, whereas the phytic concentration that we need here is something around 10 to minus 24. So again, it's our orders of magnitude, so it's highly likely that we have some kind of a still activation, cosmogenic activation of xenon happening that produces tritium. However, we can get tritium in a different way, like I mentioned. We can get it basically in many different materials. So at some point, if our materials were exposed to water or some other, obviously some vapor or something like that, so these materials can then later release when they're installed in our detector, also treated water and gaseous tritium. And like I mentioned, we need something like 10 to minus 24 mole per mole to account for something in the ballpark of this excess. We can constrain those, first of all, from the ratio of treated water to water, which is 10 to minus 17 mole per mole. And what basically it means that we would have to have a ratio of water to xenon in our detector or level of 100 ppb or so. However, from the fact that actually we see light in our detector, because, well, and from log field measurements, we know that this level should be 100 or 100 less, so at least 1 ppb or so. So we can discard that. The other way, one with deuterium, is much harder to constrain. Basically, a ratio, you can see here the same ratio for tritium and deuterium as the water one. And to extend excess, again, we need something like 100 ppb or so. However, we don't have any measurements or constraints on the deuterium level. So we try and use oxygen instead. And we get from our electron lifetime, from purity measurement, that we have a level of less than 1 ppb. Or because we don't have any direct measurement or constraint in deuterium, we still keep it as a potential maybe. And so far we have a tritium explanation. We have also another explanation that probably is much more interested in terms of physics and excitement, and this is axions. So what we consider was the most generic possible model we can think of in terms of axions. So axions that can be produced in the sun and then be detected in our detector via the axioelectric effect, basically adding another coupling here of GIE. And basically, we treated all of those models as 3 independent parameters, and where you see the fluxes as they're generated sun, and then eventually this mirrored spectra as we should detect them. And then by fitting this, we get a 3.5 sigma excess. However, if we obviously introduce tritium into our detector, basically the axion is favored only at 2.1 sigma over the background plus tritium. So hopefully we don't have any tritium. Well, because we have a fitted excess of over 3 sigma, we can draw basically contours, confidence contours, which we do. And I'm sure quite a lot of you have seen this previously. Unfortunately, so this is only a projection of the Primakov effect versus the ABC. Okay. And basically, unfortunately, the problem is that the majority of this interpretation is currently excluded by the red giants and the white dwarfs cooling rate, because astrophysicists don't really like if you introduce random axions into them, they start cooling their stars too fast. So this is quite a contentious point, or I know there are some studies that try to alleviate those measurements somehow, and basically alleviate those constraints somehow. There are quite a few other things that can actually be fitted, such as axion-like particles, dark photons, and monogenetic peaks. Unfortunately, I don't have much time to actually document them, about them in detail, but you can read about them either, for instance, about the neutral magnetic moment in our own publication, or other publications that should be presented here as well. So what do we do next? Well, we go towards XENONnT. So this is a bigger detector that we are currently commissioning. It would have a 3 times bigger active volume, would have a only 6 background level of XENONnT, and would hopefully produce results basically in early 2021, maybe a bit later due to the current situation and well, basically how it's going to work. And not only that we're going to probe this parameter space that I mentioned previously and try to discern between tritium and so on, we're going to basically have the ability to probe a big energy range between basically supernova neutrinos on the KD scale to neutrinos that will be indicated on the NEWSdm scale. And why we can do that? Because besides the much bigger time projection chamber we introduce also a new liquid xenon purification system for faster purification, a new red installation column to remove this late 214 background and try basically alleviate this background as much as we can. And with new neutron basically that allows us to tag neutrons in our detector. And this brings me nicely to the summary. Basically, using XENONnT, we would hopefully not only be able to reduce our, basically go down with our sensitivity as low as possible, and hopefully maybe detect some WIMPs. And you can read more about this in the latest sensitivity paper. And it occurred about axions versus tritium in an order of scale of several months. We will be able to determine basically discriminate between axions and tritium in XENONnT when it's operational. And after about a year or so, we'll be able to get ready to 4 or 5 sigma if the success persists. And that's pretty much it. Thank you very much. I'll leave you with this first scintillation pulses that we got from XENONnT during commissioning. So this is just one pulse. If you want to follow us, just go to one of those links. Thank you very much.
Thank you very much, Alex. Other questions or comments? Please just raise your hand or let me know otherwise that you will have a question. So I assume we have more questions also after Felix talk. We can, of course, take them, combine them. I just have the naive question. You said that the threshold is far away from where you see the signal of your detector, but still the turn on of your efficiency is extremely steep.
Yes, but it happened. I can show it to you. Okay. Yes, exactly. But this is 1 kV, this is 2 and 3 kV, and here the efficiency is still 90%. So, or basically, selection efficiency at around 90% and so on. So yes, there would be eventually some threshold effect. However, this would be happening closer to this bin rather than 2 bin.
Okay.
Obviously, if you double the analysis threshold and the excess to persist, I guess there is something there.
Right. Okay. Now we have more questions. So Jing Lai first, please.
Yes.
Just mute yourself. Yes.
Yes. Can you hear me?
Yes.
Alex, very nice talk. Congratulations on these new results. I have one question about the shape uncertainty of your background, which is that there are recent nuclear physics calculations that indicates that the dominating lead-212, lead-214, sorry, 214 is the dominating, and also maybe krypton-85 may have large systematic uncertainties in the theoretical shape. Can you comment on whether, for example, krypton-85 shape can cause this, you know, unexpected access?
As far you can see it actually here, this is why I opened the slide. So krypton-85 is extremely subdominant compared to lead-214 here. I'm not aware of any dedicated studies for low energies as we did for lead-214, but if it's so subdominant by an order of 9 to more, actually, I highly doubt that it contributes much. And the other one that you mentioned were, sorry, lead-214, right?
214.
Yeah, so for that, we did the study that I mentioned with Hau-Bin, basically looking at the uncertainty at the lower energy scale that you see here, basically the shape uncertainty on the lead-214. And you can see basically this variation of 6%. And there's basically an entire appendix that describes the calculation method that this team made. I think they published a paper recently that described this, maybe last week or so.
Very good, thank you.
Okay, we have more questions. The next one is Kalpana. Please unmute yourself.
Hi, can you hear me?
Yes.
Hi, so thank you for the nice talk. I have a question. You mentioned that tritium is produced cosmogenically in xenon.
Well, activated in xenon, yes. So.
Okay, so what is meant by that? I couldn't quite understand it. I mean, what is the how it happens? What happens? I mean,
to be honest, I'm not exactly sure about the chemical process that generates it. I think the majority of contribution is basically the treated water. So we have some water basic contamination, and eventually we remove that as well. So if you have some cosmogenic activation, you're not going to activate xenon itself. We're going to activate some other thing that is going to create treated water. I hope it kind of answers your question. Because it does not activate, obviously, atoms of xenon. So it's there is some impurity that we have in xenon that is being activated.
So it's an impurity present in the gas, in the xenon.
Yes, that's why we purify our xenon constantly, because there's entire campaign of gas purification of xenon.
Okay, thank you.
Okay, even more questions. So we can take one more question. The rest we have to defer to the coffee break. And it's Katarina, please go ahead.
So I'm wondering, no statistics. Maybe I'll let Keisho ask his question, then her question, and I will ask on Mattermost.
Thank you. I have a question.
Yes.
At this I understand that at this moment, the electron excess is can be explained by tritium background. Is this correct? At this moment.
Basically, that's okay. I can show. So this is our general, all the hypotheses that we tested. So we can explain the excess as tritium at 3.2 sigma if tritium exists in our detector. Our solar axions that you consider are favored, even slightly favored if we consider basically the tritium plus background. Compare basically 3.5 just for axions and 2.1 for combined background tritium. So yeah, so there is a potential explanation for tritium simply because we can't currently constrain the rate of tritium very well, and that's the message.
So, in summary, this excess could be from tritium background at this moment.
It is still possible, yes, especially because the interpretation as solar axioms and is, like I mentioned, is in quite contention with astrophysical observations. Because we don't have a solid handle on the tritium rates, we can't really constrain the tritium rate, so it is still possible.
So let's expect future run, okay? Future experiment, okay?
Yes, exactly.
We hope, yeah. I do hope. Okay, thank you.
Okay, thank you. I think we all hope that. Thanks again, Alex. So we have to stop the discussion here.
Okay,
we have on Mattermost. You can just answer to your to the talk that is there. So we list all the talks in Mattermost. You can just have a thread under this, and I am sure Katarina or others will have questions. Okay. Thanks, Alex.
I'll stop sharing. Okay. Thank you.
Very good. And then we move on. We stay with this topic, and Felix will give us now the theory perspective or some possible explanations. Felix, whenever you're ready, please share your screen.
Very good. Can you hear me? Can you see my screen?
Yes, all good.
Perfect. Okay, great. Hello, everyone. Good morning. And thanks a lot for the opportunity to give this talk, in particular for the flexibility of the conveners, because I changed topic last minute. Because I've been, like many others, quite excited by the XENONnT results that we just heard about, and worked on 2 papers that appeared in the past month that I want to talk about today, together with some other interpretations that have been presented. The first paper is together with my PhD student Fatih Ertas and the group of Jörg Jecke, and the second paper is together with other members of the Gambit community on essentially global fits of models of Axion-like particles. So I can be very quick on this slide because Alex has just given a very exciting and thorough presentation of the XENONnT excess. So we have this number of excess events in electronic recoils with energy around 2 to 3 keV. And there are several different signal hypotheses, including solar axions and solar neutrinos, for which the significance of this excess is greater than 3 sigma. So this is interesting. It's also important to emphasize again that there may be more conventional explanations, in particular due to an unaccounted tritium component, which also gives a reasonable fit to data. And I will come back to this towards the end of my talk. So I think it's fair to say that this result has created quite a huge excitement in the community. The paper by XENONnT has gathered something like 100 citations in a month, and there have been over 50 ambulance chasing papers over the same period of time. Also, I want to apologize for not being able to cite everyone and give credit to every idea. I will just kind of make a subjective selection of the things that have been proposed. And the first possible explanation in terms of new physics of the XENONnT excess is that XENONnT is seeing either the scattering or absorption of particles produced or accelerated in astrophysical systems. So particles produced, particles with relativistic or semi-relativistic velocities. We've already heard about 2 examples. The first one, kind of the flagship interpretation of the XENONnT collaboration, are QCD axions produced in the sun. A second possible interpretation are solar neutrinos with non-standard interactions that would allow them to scatter at the observed rate in XENONnT. Then there's also been a lot of interest on the idea of boosted dark matter. So these are dark matter particles that get accelerated through some process to a velocity of the order of 10% or so of the speed of light. And finally, you can also think of particles produced in dark matter annihilation or decay that could have sufficiently large velocities to create this kind of signal. At the bottom here, Just two examples, the boosted dark matter interpretation and the solar neutrino non-standard interaction interpretation, just to show that it's generically relatively straightforward to obtain a reasonable fit to the excess in these kinds of frameworks. But of course, the purpose really of the XENONnT experiment is to search for dark matter. So it's interesting to think about whether the XENONnT excess can be explained in terms of non-relativistic particles gravitationally bound to the Milky Way. So that in a sense, XENONnT is really seeing what constitutes the local dark matter density, or at least a fraction of the local dark matter density. This is, after all, what we're kind of all hoping for, that XENONnT will reveal to us. Now, the simplest interpretation that you could think of, which is elastic dark matter electron scattering, doesn't actually work. You don't get a good fit to data for this interpretation, even if you kind of play around with form factors and allow momentum-dependent interactions. So the kind of most standard interpretation of electronic recoil events doesn't quite work. But there are many ways in which you can make it work if you make the model slightly more complicated and arrange for additional energy release in the detector. You could imagine, for example, that dark matter has some kind of excitation and then de-excites upon scattering with electrons in the detector. This goes under the name of exothermic dark matter. Luminous dark matter is kind of the same idea, except that this is spontaneous de-excitation. So the excited dark matter particle emits a photon as it traverses the detector. Another idea that has been suggested is called Rayleigh dark matter, where dark matter actually scatters with the nucleus, but in doing so emits a photon. So all of these in principle work, but of course you kind of need additional structures, additional complications in your model. There is actually a much simpler possible explanation, which is that XENONnT is not seeing scattering, but the absorption of dark matter particles. And these then would have to have a keV scale mass and be bosonic, so that they can be absorbed in a process essentially analogous to the photoelectric effect. And there are two very well motivated candidates that would do exactly this. The first one is Axion-like particles, so particles like the QCD axion, but with larger masses. A slight subtlety here is that these particles tend to be unstable, so you need to find a way of suppressing their couplings to photons, but there are models in the literature that do just that. And the second possibility is dark or hidden photons, which obtain couplings to standard model particles through mixing with the visible photon. So for both of these particles, we have a good understanding of how they may be produced in the early universe. And they can be produced via what is called the misalignment mechanism. So the idea being that the kind of classical field starts off at a value that's different from the minimum of the potential, and then over the evolution of the universe starts oscillating in around the minimum of the potential. And these coherent oscillations essentially then source the creation of non-relativistic dark matter particles. For hidden photons, this is slightly more complicated. The misalignment mechanism actually requires a non-minimal coupling to gravity, but this has been shown to work equally well. So this idea kind of trivially gives a good fit to the excess, because what you expect is that you get electron recoils with energy equal to the rest mass of the dark matter particle. You can neglect their kinetic energy. So to first approximation, you get a monoenergetic peak at the rest mass. But then, of course, the detector has finite energy resolution. So this actually ends up giving a reasonably good fit to data. XENONnT doesn't actually show this kind of fit. They prefer to just set upper limits on this model for reasons that I will discuss towards the end. But if you just do this in a naive way, you get something that looks like the plot down here. You can already see the kind of improvement in chi-square. I'll come back to that as well. Now, the problem, as we've already heard in the previous talk, with many of the possible interpretations of the XENONnT excess are astrophysical constraints, and in particular stellar cooling. So the idea is that many of these light particles can be produced in astrophysical systems and would contribute to the energy loss of these systems. And in particular, we have a reasonably good understanding of stellar cooling rates in white dwarfs, in red giants, and in horizontal branch stars. So from these systems, we actually get strong constraints on the possible xenon one-ton interpretations. You can see that in the plot here on the right, which has in red the kind of allowed parameter region considering stellar cooling constraints, and in blue, the preferred xenon one-ton interpretation for the solar axion case, so axions produced in the sun. So this interpretation seems to be robustly excluded by astrophysics. But actually the story about stellar cooling is a bit more interesting than this, because it turns out that we don't quite reproduce expected cooling rates in observations. For example, there's the R parameter, which is the ratio of horizontal branch stars and red giants, which is observed to be slightly smaller than expected. And this leaves a small preference for additional cooling contributions. Much more significant is the discrepancy in the cooling rates of white dwarfs, which you can measure through the pulsation periods. This is actually significantly larger than expected, and you can see here a plot from a paper we wrote 2 years ago with a combined fit to different white dwarfs, where you can see that this favors, in this case, an axion-electron coupling quite different from 0 at a reasonable significance, more than 2 sigma. So there is something interesting in the context of stellar cooling as well. And now the obvious question is, how do all of these things come together in the specific case of absorption of bosonic dark matter? So let's first look at the case of hidden photons. And here it turns out that something interesting happens, because if you have masses of around 2 keV, then it turns out that the production of such hidden photons is actually very efficient, because the hidden photon mass is comparable to the plasma frequency in the cores of horizontal branch stars. So there's a resonant enhancement of this production, and the cooling rate can be quite large. And it turns out, if you look at this in more detail, that the mass and coupling strength that are required to fit the xenon one-ton signal actually predict a non-negligible contribution to the cooling rates of HB stars, which is just roughly in the range that you would need to accommodate this slight preference for additional cooling in the R parameter. So this is what's shown in the plot here on the right. The blue region is the parameter region favored by xenon one-ton, 1 and 2 sigma. And here, what's labeled HB anomaly is where you would give the kind of required contribution to horizontal branch star cooling rates. In this model, you can't say anything interesting about white dwarf cooling, because the contribution from hidden photons is actually negligible. But nevertheless, this is at least a curious coincidence and quite intriguing in my opinion. So for axion-like particles, the story is a bit more complicated, because it turns out you don't have this resonant enhancement. So the electron coupling that you would infer from xenon one-ton at first sight is too small for the ALPS to contribute to stellar cooling rates. Or in other words, astrophysical constraints are easily satisfied. However, if you allow for a bit of additional freedom and assume that the ALPS only constitute some fraction eta of the local dark matter density, then it becomes more interesting, because if there are fewer ALPS, that means you need larger couplings to explain the xenon one-ton excess. And then actually you can simultaneously accommodate the excess and the stellar cooling rates. And you can see this in the plot here at the bottom. This has on the x-axis this dark matter fraction eta, and on the y-axis the ALP electron coupling. And you can see that a combined fit to xenon one-ton, the R parameter, and white dwarfs gives a relatively strong preference for ALPS to be something less than 20% of the local dark matter density, and the coupling to be a few times 10 to the minus 13. And if we are close to the best fit point here, then really you simultaneously fit xenon one-ton and the white dwarf cooling hints, and you get a contribution to the R parameter as well. So this is certainly now not the simplest model, but it has a number of really interesting implications. A different way to show the same thing is given here. So again, ALP electron coupling on the y-axis, but now the ALP mass on the x-axis. So here, this is now, of course, again, centered at 2 to 3 keV. And you can see this now compared to the parameter region preferred by the white dwarf cooling hints, and in green, the parameter region excluded by the R parameter. You can also see in the right here how the best fit point shifts the kind of predictions for the various white dwarfs and the R parameter. So you can see that, so the blue points correspond to the case where the Axion-like particle contribution is included. And you see that this kind of reduces the tension with observations. So to make this more quantitative, you can look at delta chi-squares. For the case of only Axion-like particles, we get from xenon 1 ton alone something like 16.8 in terms of delta chi-square, 17.7 when you include the R parameter, and 23.1 when we also include the white dwarf cooling hints. If you allow for an additional tritium component to absorb part of the excess, this goes down to 8.6 for xenon 1 ton alone, but is still of the order of 15 when including the astrophysical hints. So this is a sizable delta chi-square. Of course, what you would like to know is how this translates to something like a global significance or a p-value for the ALP hypothesis. Now, this is very difficult to do in a frequentist analysis. You need to make a lot of assumptions on the kind of distribution of the delta chi-square and so on. But we can do something else, which actually turns out to be very instructive, which is to perform a Bayesian analysis. So in particular, what you can do is calculate the so-called Bayesian evidence, which is the integral over the likelihood times the assumed priors of the model parameters integrated over all of parameter space. And the idea is that if the data is in good agreement with the typical explanation for the model, the evidence should be large, and otherwise it will be reduced. And in particular, if you have two different models, you can calculate what is called the Bayes factor, which is basically the ratio between two different Bayesian evidences. And this gives you the preference for one or the other model from the Bayesian perspective. Now, in practice, this is a bit more complicated. I don't want to go into the details, but there's basically 3 steps. So the first one is to choose the appropriate priors, which should encode general expectations on the model and, if you want, previous knowledge. Then combine all the available experimental information to obtain global likelihood functions, and then use a specialized sampling algorithm like multiness to calculate the Bayesian evidence. The good news is that all of this has been largely automated in the global fitting framework Gambit, which is why we then kind of basically just had to add in the xenon 1 ton likelihood, set up the scans, and produce these plots and evidences. So here's a very quick summary of the results that we get from the Bayesian analysis. For more details, I would refer you to our paper. What's interesting about the Bayesian approach is that it includes an automatic Occam penalty. So that means that a model is penalized if it makes very unspecific predictions, if the magnitude or location of the signal is not very well constrained by the model, say. And this is indeed the case for the model of Axion-like particles, because the peak basically can be anywhere and the signal strength can also be anywhere. So there's no reason that it would show up exactly where it does at the magnitude that it does. And this actually, at the end of the day, leads to a Bayes factor smaller than 1. So this means that we find actually slight evidence against the ALP model in our setup, even when neglecting the tritium background contribution. If you include the tritium background, then the Bayes factor is even further reduced. Of course, you can now play around with the prior choices. In particular, you can somehow motivate or try to motivate smaller coupling ranges so that the xenon 1 ton signal is more plausible, more likely. And this then, of course, enhances the Bayes factor by a factor of a few. But still, we only get, at best, a relatively slight preference for ALPs. So the bottom line, the kind of take-home message here, is that Axion-like particles and also hidden photons can certainly fit the xenon 1 ton signal and also fit astrophysical hints potentially, but they certainly did not predict any of these things from first principles. at least not in any specific way. So just very briefly, what's happening next? Now, of course, as we said in the previous talk, we are all very excited about what future direct detection experiments will tell us about this. And if the excess is confirmed, then one of the really interesting things will be to measure its time dependence. And one of the reasons is that this actually allows to distinguish dark matter scattering and dark matter absorption, because the latter does not exhibit an annual modulation. However, something else can happen, which is quite interesting, which is that in hidden photon and ALP models, you can actually have relatively large inhomogeneities on small scales, things like Axion mini clusters. And this would potentially lead to a very substantial boost of the event rate for something like a few seconds whenever a substructure crosses the detector. So one should then perform a search for kind of clusters of events in these detectors as a possible way of discriminating between different models. So to conclude, there are many ways to interpret the XENONnT excess in terms of new physics. I haven't been able to review nearly all of them. But from my point of view, the most interesting possibility is that XENONnT sees the absorption of bosonic particles from the local dark matter density. And these could in particular be Axion-like particles or hidden photons, which are both well motivated and cosmologically viable, that give a good fit to the data and satisfy astrophysical constraints. Moreover, in both of these cases, you can give a relevant contribution to stellar cooling rates and account for these various hints that I mentioned. But then it's important to keep in mind that while there may be a strong local preference for these models, there's no real preference for them from a Bayesian point of view, because they make fairly unspecific predictions. In any case, I think it's certainly true. It has already been true, but it's even more true now that the next few years will be very exciting for direct detection experiments. Thank you very much.
Thank you very much, Felix. Other questions or comments for Felix? We'll wait for the hands. Felix is also available in a Zoom discussion. You can find the connection details in the agenda as well. And so, Kalpana, you have a question? Go ahead, please. Kalpana, you had raised your hand, or?
Yes. Can you hear me?
Yes.
So thank you for the nice talk. I have a question that you discussed that the bosonic dark matter candidates can explain this excess of events.
Yes.
So I want to know if the scalar dark matter particles can also explain this. Is it possible?
Yes. So indeed, in terms of, if you just look at XENONnT, then it's essentially, you get exactly the same signal for any kind of bosonic particle. So this is really a monoenergetic peak at the rest mass of the particle. What changes for scalar as opposed to pseudoscalar particles is the astrophysical predictions. So my understanding is that scalar particles have an enhanced contribution to stellar cooling, and therefore would typically be disfavored by things like the R parameter and white dwarf cooling rates. So there you again run into the kind of problem that you can't satisfy all constraints simultaneously. But from the point of view of just XENONnT, I think all of these models are equally good fits.
And we have another question from Anirban. Please unmute yourself.
Yeah. Hi, Felix.
Hi,
it was a nice talk. I have a question. Like in the end, you mentioned about this the passing of Axion mini clusters through the detector, which can enhance the signal by maybe many orders of magnitude. Do you have any like estimate like how frequent that kind of event could be, or
So for the case of Axion-like particles, I don't. For the case of hidden photons, this is actually something that was looked at by my collaborators, so the group of Jörg Jecke, and they estimate that these events would happen several times per year. So this is not extremely rare or extremely unlikely. This is something that should happen within the runtime of a typical direct detection experiment.
Okay, and how big are these clumps?
That's a good question. In terms of spatial dimensions, order hundreds of kilometers. So passing time would be of the order of seconds. In terms of the overdensity, I'm not exactly sure.
Okay. Thanks.
Thanks.
And thanks, Felix, again. There are no raised hands right now, but again, Felix has a Zoom session and we can discuss on MetaMost. Thanks, Felix.
Thanks a lot.
And then we move to the last talk of this session, which is from Mariano, also an exciting new development, which is the SENSEI experiment. Whenever you're ready, please share your screen.
Great, thank you. All right. Okay. Can you see my screen?
Yes, that's good. And I can see you and I can hear you. Please go ahead.
Great, thank you. So thank you for the collaboration, for this opportunity. My name is Mariano Cababie. I'm a PhD student here at the University of Buenos Aires in Argentina. I'm talking on behalf of the SENSEI collaboration. And I'm going to talk you about the SENSEI experiment and ultrasensitive search for Sub-GeV dark matter. We're going to talk about the SENSEI experiment itself, about the Skipper CCD, which is the device that we use to get our dark matter searches. We're going to talk about the last result we had on this year, which was about April this year, before the COVID, at least here in the Americas. And we're going to talk about the perspective to the future in the next year for SENSEI. So the SENSEI collaboration is a collaboration among some universities and institutes in the US, from Fermilab, Stony Brook, and the University of Oregon. We also have people abroad, which is, I don't know if you can see this. Oh, sure, okay. From the Tel Aviv University in Israel, from the CONICET in Argentina. We are a fully funded collaboration by the Hagen Simmons Foundation, and we have leveraging R&D support from the Fermilab Laboratory. So in the last years, from the beginnings of SENSEI, we started from the demonstration of subelectron noise in a SENSEI prototype up to the last news that I told you, which was the dark matter search with an underground round of the SENSEI first grade science Skipper, which is the final form of our devices that we're going to use in scale when we go to SNOLAB in the future. In the bottom here, you can see from the beginning in 2017, the subelectron noise. You can see the 0, the 1, and the 2 electron peaks that you can read in the CCD without having any doubt. If you have 0, 1, or 2, I mean, you have some significance. And you can see this both for very low energies. By this, I mean 0, 1, or 2 electrons, or very high energies when you have around 777 electrons. If you continue on the bottom in the center, you have the 2018 result, which is a high cross-section dark matter constraint, which was done with a SENSEI prototype on the surface. And on the bottom right, you can see what is the SENSEI iDMEu last result that I'm going to talk about you in a few minutes. So what do we look for? So what we look for is dark matter and electron scattering. We look for electron recoils in the Sub-GeV dark matter range in a Skipper CCDs. So that's what SENSEI is about. So our benchmark models will be dark matter electron scattering and dark matter absorption. So for example, we can have a dark matter candidate that may interact with one of the electrons in the valence band, and you can promote this or more of one electron to the conduction band depending on the energy of the recoil. That creates a whole electron pair, and the whole will be captured by the pixel of the CCD as its device to do that. So what you have is the CCD as an ionization detector. You have the matter interaction or absorption. In any case, you have a matter, a heavy photon, for example. You have the energy transfer via electron recoil. The ionized holes are captured by the potential well, and then you can read that signal after exposure is finished. So in a skipper CCD, I'm going to talk about this later, but you have a pixelated array, which is a silicon array. You have all the charges captured on in each of these pixels that are microns long. And then you read this row by row, you put them into the serial register, which is this horizontal shifter over here, and you read pixel by pixel into the readout stage. And lastly, the Darman arrangement, which is pretty obvious, is between 1 and 1,000 MeVs. That is a Sub-GeV Darman range, and it's also in the EV under matter absorption. So let's talk a little bit about CCDs. CCD, basically, what you need to know is that we use it for ionization, and it is a pixelated silicon array. So each of our devices is 2 grams per device of high resistivity, fully separated silicon. We have a very high charge collection and transfer efficiency, which is very good when we want to analyze the signal and do the analysis that we do to make the constraint that we do, all the excesses that we look for. And we have 5.5 megapixels of 5 microns per micron, 15 microns per 15 microns per almost 7,000 microns of thickness. On the bottom left, you can see what is the cross section of one of the pixels. You have a free-phase pixel structure, which is typical for CCDs. You have a barred P channel that shapes the voltage between the pixels, so you can capture the holes that you want to capture. You have a sensitive volume where the ionization takes action, and you have a bias voltage that you use to deplete the CCD. And here you have a more illustrative with more descriptions. The part of the CCD, you can see the free voltage that you have both in the vertical and the horizontal shifter. You have the output stage. You can look at this. It's another paper too that we already published. But basically what you need to know is that the ionization itself is produced in the active area over here, in the pixels of the active area. And those are moved to the serial register to then be moved row by row. They are moved row by row to the serial register, and they are moved pixel by pixel to the output stage where you read them out. So what is the skipper CCD? So as I already told you, we work from the 1 MeV to the 1,000 MeV dark matter range, or in the EV dark matter range. We're talking about dark matter absorption. So what we have is very small signals, and we're looking for electron recall. So we have a very small signal. So we need a very low energy threshold. And that's where the skipper technology comes into, because what the skipper technology allows you is to read repeatedly the same pixel, so you can actually achieve sub-electron noise without destroying the charge that you are reading on each pixel. So what you have is that, for example, when in a conventional CCD, you have a 2-electron noise. In a skipper technology, with use of skipper technology, you can achieve sub-electron noise down to, for example, 0.1 electrons. So your energy threshold goes down to 1.2 electron volts, which is the silicon bandgap of the CCD. So you have a very low energy threshold, which drastically increases your sensitivity in the attribution of energy. On the right, you can see the images that depict this. For example, in the top, you have what is the readout noise versus samples per pixel plot, which shows you how the readout noise goes with this function, which is the fact that you have the readout noise for n samples. When you read repeatedly the same pixel n times, the noise that you actually have is reduced by a factor of the square root of n of what you will have if you only read once. And on the bottom right, you can see the picture that I told you, but it's pretty good to show the idea that we are actually achieving sub-electron noise in this case. So what we do, I already told you, in conventional CCD, charge is moved to the sense node, area once, then it's read and lost. So what happens is that when you have longer integrations in a conventional CCD, you can reduce the noise, but you cannot beat the 1 over F noise, which is the low frequency noise. And it's one of the main noises that you have in a CCD, in a normal conventional CCD. And I already told you that skipper CCD, what it does, it moves towards and backwards the same charge, so you can actually read it more than one time. What it uses is a sense node that is floating in the other. You have the zero register on one part, and what you have in the other part is a floating sense node with the amplifier and the output stage, where you create the signal and transform it into a voltage. So simply what you have is a place where you take the pedestal, which would be the baseline of the signal of your pixel. You have all the charges that are summed up in the summing well, which is one of these pixels that are in the end of the serial register near the output stage. What you do is move all these charges through the output gate to the sense node. You then take an image, you measure the signal for a particular time, and you can reduce those. That's what's happening in a conventional CCD. What happens when you are using a skipper CCD is you're going to do this movement backwards and forwards, and you can actually repeat without destroying the charges and copying the amount of charges that you have in the sense node, in a floating sense node in the other part of the CCD, where the amplifier stage is. So what do we mean when we say that we reduce the 1/f noise? What we say is that we have for example, if you have a high frequency noise in a regular CCD, this compensates both in the pedestal and in the signal, both in the baseline and the signal, so you don't have that kind of noises affecting your signal and basically your real noise. These are very, it's illustrative, right? But you have the high frequency noise effect and the low frequency noise effect, both in the top and the bottom. What happens when you have a skipper CCD is that you're taking multiple times the same. You can reduce your integration time, but you can take multiple times the same pixels. So what happens is that you auto-compensate because you're taking the pedestal multiple times and you're measuring the signal multiple times. So at long term, the effect of the low frequency noises compensate with itself, both in the pedestal and in the signal. And you can achieve this reduction in the 1/f noise. So let's talk about our setup. The location and shielding. The setup is Fermilab. It is in the shallow underground Minos site. Maybe you know about that. It's been inside the Fermilab National Laboratory. It's 107 meters below surface. So being underground reduces the moving environmental radiation a lot. And then to reduce the gamma environmental radiation, we use lead bricks that surround the CCD. Inside the CCD, inside the vessel, we have 1-inch bricklets, which are this over here. That's around the CCD in the inside. And then we have a lot of CCDs, a lot of bricks, bricklets, lead bricks of 2 inches that are around the CCD outside it that we added this year. So we operate on 145 kelvins and we have a high PICO regime so we can reduce dark current without generating any undesired effect that affect our signal, just as CDI, which stands for charge transfer inefficiency. Okay, so lastly, we can talk about electronics and the inside the vessel. On the right, you can see what is inside the vessel. You have the CCD over here. You have the lead bricks that we talked about. We have the sense that sense the temperature. And it's important to understand that we have an electronic that was specifically designed by engineers in Fermilab to read out the skipper CCD. This one is called the LTA board, which stands for low threshold acquisition. And the fact that this board allows you to the multiple reading of different CCDs from one or more computers, so you enable the scaling of the number of CCDs that you can use, and you can think about doing this in a massive scale, which is our plan, right? Now, starting talking about last result, let's talk about the quality cuts. So we have a lot of images here. You can see what is a normal image that we use here. This is a fifth of a quadrant of one of the 22 images that we took. So it's a very small portion, but it's a very good idea because you have an electron over here. You have some gamma ray electrons that were produced that are the most, these that are kind of roundy. And you have, for example, here a mu that is cut over here. So the basic idea is that we use a lot of quality cuts, that allow you to mask some part of the CCD that you don't want to use for a signal because you know you have some, for example, bad pixel or dark spikes, which is some pixels or some columns that have more, that generate more oftenly dark current or from thermal agitation because of defects. You have zero register hits, which are these over here, which are this. That happen when a high energy event interacts with the CCD, but in the zero register, so that event is confined in the zero register. It goes broad and it cannot go into the active area, so you have something that goes in one direction. You have to max that out. You have bleeding, which has to do with the CDI. That is when some charge is left behind. You have a track of high energy events, for example, over here or here. You have the halo, which is something new. The halo is a correlation between the low energy events near high energy events. We say that it's new because it's not described in the literature, and we are actually doing a lot of work trying to understand what's going on there. This is in the paper. I'm not going to talk about that in detail here, especially because we actually don't know what's going on. But what we know is that we have some correlation in space between the low energy events and high energy events. And finally, the last that is worth talking about is the loose cluster tool. The loose cluster, which is something that we use to the two-electron analysis. What we do is we don't use for the two-electron analysis zones where we see a lot of one-electron events. We say that we don't know why do we have some zones that have an excess of one-electron events. We kind of expect these things to happen because of defects and stuff. So what we do is not use those for the two-electron analysis. And by two-electron analysis, I mean when we look for dark matter in that energy range. And we have others masks that what give you is this. So this to give you an idea, the magic is done by the DS9 software that has some scaling and color stuff, but the idea is that we use a lot of masking and we get rid of most of all the image when we try to do our analysis. All of these masks are fully described in the paper that was published. I think it's a preprint, it's about to be published. It was in April this year. And it's in the reference down here. Okay, now let's talk about our result, data and some specifics. So we have a blinded data set of 22 images that was taken from February 25 to March 20. These images were 20 hours of exposure and 6 hours of readout each. We have a total exposure of 20 gram days, which is pretty low compared to our experiments, but we are very sensitive on this gram and on this range of energies that we use, which is 0, 1, 2, and 3 electrons. On the top right, you can see an image of how the data looks. I mean, this is what we do. We take an image, we take the pixels that have 0, 1, 2, or 3. We look at the picture, we look at the pixel that we don't mask out. We find mostly 0, 1, 2, and 3 electrons. In this case, in this search, we were lucky, and we didn't get any free electrons in a single pixel search. So this is what we look like when we are looking for 1 electron or 2 electron cats. We use 300 Skipper samples, which gave us a 0.14 electron noise. And it's important this part that we want to assert the fact that we have a lot of improvement from 2019. So we're looking for the future in 2021 and improve the same way, so we can improve our matter constraints and look for excesses in a better way next year. So what we had is 20 times more mass than in 2019. Our background radiation go 3 times less than in 2019. So now we have around 3,000 events per kilogram per keV per day in minus. We have a single electron event rate as low as 1.65 10 to the minus 4 electron per pixel per day, or 450 event gram day, which is 20 times less than 2019. This was crucial to increase our sensitivity, and it's a world record in silicon devices. And we have from 8 to 35 more effective exposure because of all these things that we could improve from last year to today. So what this gave us is world-leading constraints on dark matter electron scattering for the light mediator, which is in the top right over here. This gave us world-leading constraints for the heavy mediator in the top left, up to 10 MeV over here. This gave us world-leading constraints for dark matter nuclear scattering, which is the Migdal effect. It's in the bottom left through light mediator from 600 keV to 5 MeV, which is over here, and gave us world-leading constraints for dark matter absorption of electrons, which is the bottom right from the silicon bandgap to 12.8 eV. So what do we have for the future? How many minutes do I have left? Okay.
You have about
so what do
2 minutes, 1.5
Okay, thank you. So what do we have for the future from the demonstration of a 0.068 electron noise in a SENSEI prototype? Well, I mean, we went through all this. What do we have for the future in 2021? So we have our science detector, and it's working. This is very best part of it. So the next step that is going on right now is the production, which is in progress. Here you can see the vessel, the 3D model of the vessel that we're going to install in SNOLAB. And what we have right now at Fermilab assembling it. You have more parts in the 3D model, which these are going to be the flex cables or the structure, and what it looks like when you assemble it. And here you have some idea of the 3D model of final device. So we are assembling our vessel that we go to SNOLAB. We expect a lot because we found out that when we increase the shielding and we decrease the background, we have a lot of good results. So we are eager to see what goes on in SNOLAB. And some more news, we have a phase 1 system full operation in SNOLAB since December of 2019. Here we have a picture of, from left to right, Zhou, Mura, Kevin Cook, Guillermo Moroni, and personal staff from SNOLAB. That was on December. They installed one CCD, and it's been fully operational since then. We're doing some tests, trying to understand the background, how the CCD works there, and all the logistics that it has to do with SNOLAB. Our final goal is 100 grams. We have 2 grams right now, both in SNOLAB and in Venus. And we're going to do our deployment stages. We will produce some CCDs. We're going to test them as Fermilab. We're going to send them in a quarterly way, especially nowadays that we have a lot of restriction because of COVID lockdown, the pandemic, right? So the results will be presented gradually as long as we are increasing the mass. So the SENSEI should be deployed by the end of 2020 or the beginning of 2021. You will hear news about this new result is not up, hopefully. And just to summarize, just to talk about the future, I want to mention the SENSEI, the DAMIC, and the SCUR experiments that are, the 3 of them are skipper CCD-based experiments from SENSEI and DAMIC, which are and in the SCUR experiment, which is a joint effort between the SENSEI and the DAMIC-M collaborations. Oh yeah, and they have, for example, the SENSEI has 100 grams gold, DAMIC-M has 1 kilogram, and SCUR has 10 kilograms. And I want to remind you that 10 kilograms is about 4,000 CCDs. We now have 1. DAMIC had a lot more, so we are looking eager to see how this goes in the next few years. Thank you.
Okay, thank you, Mariano.
Oh, thank you. I didn't hear you about the time, sorry.
Other questions or comments for this talk? Yes, Katerina, please.
So this is really impressive. It's very nice that already with a prototype you can get world-leading constraints. So I have a question that is maybe, well, 2 questions, and maybe from an uninformed perspective. The first one is whether you have any kind of irreducible backgrounds that you have to worry about as you go down in sensitivity for the invisible particle or dark matter electron cross-section. So in the plot on your last slide, for example.
Yes, that's a very good question. So yes, we have some irreducible background. It is very low though for 2 electron, 3 electrons. For the 1 electron is pretty background dominated. What you have, for example, is dark current, which is 1 electron charges that are generated from thermal agitation. You have something that's called Spirit charge that in the last month we made some efforts and drastically reduced that. Those are charges that generate when you clock the voltages, when you try to read them. And we have this, for example, these 1 electron events that are generated near high energy events. But the good thing is that when we go background, we can mask a lot of this and we won't have any of these events. These are the 3 things that come to my mind. But for example, in the case of the dark current, which is completely reducible because it's physics, the theoretical limit is that you can have 10 to the minus 7 electron per pixel per day. Right now we are in 10 to the minus 4, so we still have 3 orders of magnitude more according to Janicek. So yes, we have some, but we are pretty sure that we can reduce this a lot more.
And if there's no other questions and people are not super keen on coffee, I'll ask another one.
Sure, go ahead.
Okay. And the other one is more a psychological question. So once you reach your key milestone that you'll reach with SENSEI in 2021, what is the motivation? How do you convince people to go over to Oscura? Like, well, what's your argument there?
What's my argument to go to Oscura, you mean?
Yeah.
I mean, we still have a lot of work to do. I mean, in the terms of Oscura, I would say that SENSEI is kind of a prototype, right? I mean, it's like 100 times less exposure. It's a collaboration between, we are a small collaboration. Oscura will be a very huge collaboration. We'll have a lot of results. We're gonna see a lot of things that we can't see with SENSEI, and we have a lot of people to work with it. And it's a very huge collaboration. It's a very huge effort between all the people that work with Skipper CCDs. So I think that's the more exciting thing, that there are a lot of things that are going to happen, and a lot of things that are going to be done in the matters of the technology and the capabilities that we have to build these kind of experiments that has never been done before with solid state CCDs, right? I think that's the more exciting thing, and I think that's the thing that you have to have in mind when you are talking about Oscura and the future. Yeah, thank you for the question.
Thank you, that's interesting. It's not a yes or no or correct answer, it's just your perspective.
Right.
Okay, thanks Katerina, thanks Mariano. So I suggest that there are no raised hands. We get a coffee now. What we will do is we will just pause the recording, switch off the cameras, and we meet again here at 9:30 CST, so in 10 minutes. And again, speakers are invited to check the Mattermost channel in the meantime, because I had a question there, Felix. See you in 10 minutes.
I'm on it.
Can I try the audio? I'm the next speaker.
Yes, absolutely. Please try sharing screens, audio, video.
Okay, thank you. Can you hear me? So
I can hear you, yes, but that's all I can.
Yes, yes. Just a moment. I switch everything on. So this is the video. Should work.
Yes, video works as well.
And then let's see the screen. Do you see it?
Yes, excellent.
Okay, so I will say like that. Perfect.
Perfect.
Thank you. See you there.
Also, if the other speakers want to try the screen sharing, so we know that we're ready for that. I don't know if we have, I think Florian, I don't remember if he tested at the very start. But we at least did see the camera.
Yeah, I tested in the morning before.
Okay, good.
That worked fine.
So we need the PICO speaker now. Every time I reload the page, my browser crashes because there's so many sessions.
I grab a coffee, come back. Huh?
Yeah, absolutely. I'm gonna email the PICO speaker now. anyways, it's time to resume the session. And our next talk is Gaia Lanfranchi with the iDMEu, a new initiative for dark matter community. And we will write on your slides when you have 2 minutes left. So you'll see a little red text appearing.
Okay, so can you hear me?
Yes, we can, thank you.
Okay, so I start. So thank you a lot. Thank you for this opportunity to present you for the first time this iDMEu expression of interest, which is an initiative for somehow structuring dark matter searches in Europe and beyond. And this initiative is taking shape during this month, and I will try to explain you what it's all about. This initiative was started by a combined meeting that the three consortia related to accelerator physics, nuclear physics, and astroparticle physics did sometimes in October last year in Orsay, where they met together in order to try to understand if there were ways to organize a sort of common platform to seek synergies for different topics. For example, search for synergies about analysis interpretation of results of a broad spectrum of topics, synergies for theory models, technology changes, data sharing, software and computing, and also to try to build up a sort of unique communication towards the general public, because this is something that is felt to be very important. At the end of this meeting, that was very well represented by many high-level representatives of the three communities, was the open call for a novel expression of interest, and one of them is actually our expression of interest, iDMEu, which is essentially an initiative for trying to facilitating communication and results sharing about dark matter in Europe and beyond. Somehow, we would like to aim to be at the crossroad of different communities, so not to be confined in just one corner of the exploration range, but try to put together a large variety of communities that we heard in this session is actually very lively, very active, and sometimes what is missing is a cross communication. And this is all the four colliders, fixed target, bin dump, direct and indirect detection experiments, as well as dedicated Axion and ALP searches. And so we felt that a broad approach to this kind of arguments was needed. And the only way to go towards this aim is to create a permanent platform where all the main representatives and also all the interest people can participate actively, and we will try to organize in a structured way a sort of results sharing and discussion. So why we felt this was important? Because I mean, the problem here, as we all know, is that as soon as we move beyond the WIMP paradigm, we are lost across about 80 orders of magnitude to explore. And we don't have any clue. We have some models that points here and there, but in reality, we don't know where to look at. And therefore, we cannot simply have a single experiment to try to exploit these extreme large of mass ranges. And therefore, we need to talk together and to involve different communities that could possibly span as much as possible over this broad range. The communities are very far apart because, for example, the accelerator-based community very rarely talk to the dark matter direct detection or dark matter indirect detection community. And more we feel the need also to include astroparticle community because, as we heard, for example, from Felix' talk, these bounds from astrophysics are getting more and more important for all these kind of searches. So we have to find somehow a sort of common language in order to exchange results and understand each other when we present results. So we know dark matter is at the heart of many important fundamental questions in particle physics. It's not only an important issue per se, but could be a topic that can be deeply connected with other important open questions like the strong CP problems, the active neutrino physics, the origin of the neutrino mass oscillation, and so on and so forth. So a broad approach is also interesting for this respect, to try to understand how we can build a unified picture of all these open questions all together. And this clearly the theory community will play a major role. So if we start this journey across the orders of magnitude, the first order of magnitude that we can explore is the QCD axion, which is somehow an excellent dark matter candidate if it has a mass between the micro and the milli electron volt mass range. Motivated extension of the axion is the ALP, and this allows us to also enlarge the possible range. And to explore this paradigm, we have already a sort of synergy and complementarity across very different communities. As you can see here, this is the standard searches performed at Axion ALP dedicated experiments, where there is a very lively community. Every year there is a new result coming out, and they are deepening, investigating the standard QCD axion band. We have an important contribution from the astroparticle realm, because they are using the Big Bang nucleosynthesis, the CMB, the X-ray, the supernova, solar lifetime to put constraints on these couplings of axion or ALPs with photons as a function of the mass. And then we have also contribution from the accelerator community that is starting very lively to explore a range which is inaccessible from the other communities, which is somehow the MEV-ish range. So you see that already here you find a very nice way of exploring together somehow something like 20 orders of magnitude in mass. And clearly, there is a lot of work to do. We have to understand better all the bounds from astroparticle, and in particular, we have to keep the map updated in order to guide new proposal towards still uncharted parameter space region. So this somehow could be two of the main goals of this initiative. Ultralight dark matter, we heard before from Felix, these exciting results from Xenon and how these can be interpreted in terms of ALP or hidden photon. And even in this context, we have a very lively exploration search over different communities. We have a large part of astroparticle, astrophysics, and cosmology. We have the Axion experiments that can explore ranges in the range of 10 to the minus 12, 10 to the minus 10 MEV. We have the dark matter detection, where this is not updated, doesn't include the xenon 1 ton, but you heard before how this can be compatible with a possible dark photon hypothesis in terms of absorption. And here you see in one shot all the contribution from the main player in the game. So if you want to understand who else could say a word, you can look at this plot and say, for example, there are other candidates that could possibly in the future explore the same range as xenon. In the large mass range, you have, again, accelerator-based experiments that are also somehow extending their potential well below the MEV threshold that seemed to be impossible until only a few years ago. In particular, LDMX and E64 are really pushing forward the search for dark matter in a range that was considered inaccessible to accelerator-based experiments. Moving more towards the standardish WIMP mass range, we face first of all the range of MEV-GeV that is currently poorly explored. Still, there is a lot of effort, but still somehow there is a lot of parameter space still unexplored in the MEV-GeV range from the direct dark matter experimental effort. Because it's difficult, because it is a range that is typically very difficult, and there is a fantastic increase of initiatives that are piling up in the last years trying to explore this range towards the neutrino bound below the GeV threshold, but still you see that you have several orders of magnitude to explore. The community here is very active. There are 15, 20 experiments currently running, more than 1,000 scientists, but it's very it's nice because the pattern is essentially done by small, medium-scale experiments, and only 4 experiments are counting more than 100 people. So the pattern is very different with respect to accelerator-oriented search. And they are using very different technology, and so clearly this immediately creates a network link with solid state and nuclear physics. There are many laboratories involved, in particular Gran Sasso and SNOLAB are playing a major role, but clearly this community that is represented in this dark matter expression of interest by 3 scientists that you see in the listed at the first page, is also very scattered. So I think that it would be useful for everyone to have a way, a platform where we can exchange results and discussion, and so the communication is really needed to be improved. So what this community would like to do, what they have is the compilation of experimental results in certain scenarios and models. But what is still needed is a sort of data repository, somehow intertwined with the theorist, in order to interpret the same results from a different theoretical point of view, as we heard from Felix before. So the same results was interpreted as an Axion-like particle or as a dark photon, somehow to structure a bit more the effort, not only to interpret with different theory models, but also to try to go beyond the community and to create a direct link with accelerator, for example, and direct detection. So the question is how to move beyond, and you can move beyond only by specific models, because if you don't assume a pattern, a framework, you cannot talk together, you cannot exchange results. Each one is in its own frame of reference. So very minimal approach is, for example, assuming this vector portal with an hidden photon, and this has been used largely in the last years in order to compare direct dark matter detection with astroparticle and cosmology, and with the production of possible dark matter candidates at colliders and or fixed target beam dump experiments. And the effort has been done to put together these results, that this was done in the framework of the physics beyond colliders that you might have heard about. It was an initiative somehow triggered by the CERN management in order to try to expand a bit the physics case from the LHC to see what can be done at accelerator-based experiments that is interesting also for other communities, for example, the direct detection communities. And so we produced this kind of summary plots where you see together within a given theory framework, in that case is dark photon 1, plotted together results coming from, for example, Bell 2, which is a collider, a plus and minus collider, but also you have proton beam dump, electron beam dump, like current electron beam dump, Na64 at CERN, future electron based, is not a beam dump, but always extracted beamline with electrons, LDMX at CERN possibly, but now we know that probably will go to SLAC. And all these compared with the relic density and also with the direct detection searches like super CDMS, Xenon, all the results from Xenon. And we heard just before my talk the fantastic reach of SENSEI, not only in 2 grams, somehow instance, but even more importantly in the 100 grams instance that will be possibly running in a few years' time, that we really compete with LDMX in the same mass range below the GeV threshold. So you see, this is the kind of somehow combination of different community that we can possibly do in a given theory framework. Clearly, the theory framework can change, and the challenge is to try to keep updated with the most recent theory advance. So we move towards the WIMP. WIMP is somehow much more established community, large experiments that are doing a fantastic job. They are pushing down to the neutrino threshold, the limit for dark matter with thermal origin. We are understanding also that these detectors, thanks to their large mass, can play a role also in the search for neutrino-less double beta decay. So this is very nice, and put a direct link with the neutrino communities. And even in that case, we can create a synergy with colliders. And this is a very nice plot that was produced by the CMS collaboration, showing somehow the interplay between Atlas and CMS and direct detection community within a given, again, theory framework. Now, there has been a lot of discussion about the use of a specific choice of decouplings that has been somehow decided by the Atlas and CMS collaboration. They are using coupling of the order 1, which can create a community. So now the two collaborations are moving forward and are trying to investigate their sensitivity for smaller couplings. And this is an effort that is currently ongoing within the SNOMAS activity that is going to produce results in a year time that will show also the potential of these two collaborations for dark matter searches where the coupling is relaxed to be much less than 1. So you see here again which kind of discussion are in the field. Clearly, the main player here in the game is the cosmology. Dark matter is a cosmological object, and it would be very nice to try to create a much more direct connection with, again, a very lively community that is behind that, both theory community that are studying the galaxy formation, evolution, large scale structure formation, all the CMB computation. You have seen the Big Bang nucleosynthesis, the Lyman alpha, the intergalactic medium. So there is an infinite amount of work done there that can clearly help us experimentalists to try to pin down the more probable, more plausible ranges for dark matter searches. And the indirect detection is even more lively. So you have another spectrum of detectors that are investigating in this particular period ranges between the 10 GeV onwards. So this means that they are more compatible with the standard WIMP paradigm rather than the light dark matter searches, but they are very aware about the fact that there are several frontiers somehow they are bounding their current reach. One is the MEV-GeV dark matter search that we saw before by direct detection and mostly extracted beamline experiment. There is the frontier of going down in coupling. This is the same effort that is currently being done by Atlas and CMS. And then clearly there is the black hole and the gravitational wave frontier that is moving towards a much larger mass. So again, there is a plethora of excellent experimental results, but again, what is needed here is maybe a better coordination, map the community, try to have a place that could be a website, a meta repository where we can share results, whatever is possible, harmonize them among themselves, but also against other community, and possibly ask a question and to try to improve on all these kind of also model interpretations. Last but not least, the neutrino detector are playing and will be playing more and more a big role in dark matter searches, in particular for dark matter models, assuming that the annihilation happens in the sun. And here you see the super Kamiokande boundaries that has been put, and they will going to improve with Hyper-K, but even with Dune. And so even this is a very interesting community to keep on board, because in the coming years they can play a major role. So this is somehow a sort of very short, brief journey across the topic that we would aim to touch. Clearly, this is an effort that requires a community building. It's not something that can be done only by few people. Community is very active, but is also far apart. So first of all, we need to have a common place where we can discuss together. And we will build up a website, we will build up a repository, but all these will be discussed together once we will have the first kickoff meeting that will happen probably by the end of the year, in which we plan to involve different communities, the dark matter at the LHC, the physics beyond colliders, the dark matter direct and indirect detection experiments, neutrino experiments, Axion-like community, but keeping a very strict connection with the particle theory, so CERN theory department and others, and astroparticle theory. And here we want to profit of the fact that this European Consortium for Astroparticle Theory has CERN as a hub for the next 5 years. So we have all the best experts in astroparticles somehow around CERN. And so we would like to have to profit of this energy as much as possible. On more technical side, we have already established connection with ESCAPE, which is a European Science of Cluster of Astronomy and Particle Physics ESPRI research infrastructure as far as the data storage is concerned, FISTAT dark matter community, and other tools that are already currently used in specific places. So just a few words about European Consortium of Astroparticle Theory, because yes, I'm almost done. This is an effort that has been initiated about a year ago. The director is Gianfranco Bertone from the Netherlands and is helped by a steering committee. In the steering committee, there is Silvia Pascoli, who is one of the proponents of this specific dark matter initiative. So the link is natural. But we have also inside Gianfrancesco Giudice, who is the theory department head here at CERN, that could certainly create a natural link with the particle theory. And UCAP endorses this expression of interest and looks forward to contributing to its success. So we plan to be bounded and linked together, and they will have their own inaugural symposium for next year. We will have our own kickoff meeting, but certainly the two communities will be strictly connected. We recently received an official message from the three chair of the three community, APEC, ECFA, and NUPEC, where all this effort started, and they somehow endorse our effort, and they plan to help us in the organization, in the dissemination, in the setting up a website, in community-wide calls, and awareness on our scientific communities, and also to make this initiative known within our institute, home institute, for example, and policy-making bodies, which is very important for the lives of all of us. And they plan also to have dedicated sessions to the next common events of ECFA, APEC, and NUPEC, where progress can be presented. So this is very important for us because we needed to have their endorsement before moving forward, and now we have it, and so we can move forward. So this brings me to the conclusion. We need to have a broad approach for dark matter for sure, but also for similar big open question in particle physics, because now we are really somehow experiencing the failing of the so-called somehow sort of standard paradigm using WIMP are somehow fading away, and a bit as a unified theory, clearly experimental wise, still there is a lot to do. And we need to talk together. We need to talk together to try to find a new direction, find new paradigms, collaborate, try to drive the theory and be guided by them towards new avenues, if you want. So we plan to have the first kickoff meeting by the end of the year. We will send you news, more news after the summer. If you want to get up to date with our activity, you just sign up to this Indico page. That is the Indico page of our expression of interest. And with this, I thank you for your attention. If you want to continue the discussion, you want to ask questions, I'm available today in this Zoom link between 12 and 13. Thank you very much.
Thank you very much, Gaia. This is an interesting initiative. Well, I'm biased, but
you are there, so you are in.
So we have time for one question.
Probably the initiative is still too fresh, but
Yeah, there's what to think
sure we will have time and occasions if you're interested to follow us to discuss at length, because everything is still to be set up. So completely open to suggestion and comments and criticism as well, because we learn from critics. And in any case, if you have questions, I'm there for an hour later on, so as you like.
Okay, so I think we will defer the questions to the Zoom room, and we can move to the next talk. That is Florian Reindl, another one of the names that was in the previous talk,
Yes.
on the COSINUS experiment, or COSINUS. I'm not sure how to pronounce it.
Okay, I try to share my screen.
Yes, we can see it now.
Okay, so you see it, right?
Yes.
Yes, okay. So yes, so I will talk about the COSINUS experiment. We pronounce it in the German way. So thank you for the organizers for having me here. COSINUS is a cryogenic dark matter search with a sodium iodide target. So we've heard a few talks about direct detection already, and I think you will agree with me that we are facing the challenge of detecting a signal which is quite rare, which is featureless, at least this classic WIMP signal, featureless in the sense that we don't have a bump or peak to find, and we are talking about recoil energies in the kV range at most. So, and I just want to bring to your attention that, of course, one signature one can use to identify a dark matter signal is the modulation, and this comes from the fact that the Earth orbits around the Sun. So we change our velocity relative to the dark matter halo throughout the year, and one should see a modulation of the event rate with a period of 1 year, peaking in the beginning of June. And very often this is called a smoking gun evidence. But talking about the modulation, you of course are immediately at the Dharma Libra experiment. So just as a reminder, so this experiment uses 250 kilograms of thallium-doped sodium iodide crystals. The detection principle is straightforward. So you have the crystals, a particle interaction in the crystal will emit scintillation light, and you measure this light with photomultipliers. It's quite old direct dark matter search, taking data since mid of the 90s, and it got a recent boost in interest, I would say, again, because they lowered the threshold from 2 to 1 kV electron equivalent. So why is this experiment so famous? Well, because of that. What you can see here is the event rate with the constant part subtracted as a function of time. And you will see by eye that there is a clear modulation of your data. And if you fit it, which is the black line, then...
For a minute, your slides are not actually moving. I don't know if you're in full screen and you're on a different screen right now.
No, I'm not. Oh, they are not moving.
No.
Okay.
We're still seeing the first slide on
okay, then
PowerPoint.
You have to share your entire screen, not just the app.
Yes, okay. Okay, I will share the entire screen then. Okay. Now you see the entire screen?
Yes.
Okay, so, okay, I'm sorry for this. So now the slides are moving, right? Yes, okay. So, okay, I was at this slide. The first ones were not so important. So this is the very famous Dharma signal. And you can see by eye that there is a modulation in the data. And well, the statistical significance, if you combine everything, is 13 sigma, so quite large. Another way to look at this modulation signal is to plot the modulation amplitude as a function of energy. And you see that above 6 kV, there is no positive modulation amplitude, and all the fun starts below 6 kV with the highest amplitudes at the very lowest energies. And this was why the lowering to the 1 kV threshold was so awaited for. So do we see a dark matter signal in DARMA? Well, statistics is not an issue. Also, the period and the phase match what you expect for dark matter. And if you turn the argument around, there's not a really convincing non-dark matter explanation. So, well, why is this not established as a real dark matter signal in the community? Basically, all of the other direct searches exclude DARMA. So, and just as a reminder, this tension, if you compare different experiments, you have to do some model assumptions, in particular, if those experiments have a different target. So one word about the unknown. So if you write down the differential event rate, you see that there are two main ingredients. One is the dark matter halo and its velocity distribution, and the other one is the cross section. So from a pure experimental point of view, if you want to test DARMA in a model independent way, then the ideal way to proceed is to go with a sodium iodide experiment. So, and if you look to this, well, triangle of direct dark matter detection, this is my version of it, where you plot the experiments according to whether they use a phonon, an ionization, or a scintillation light signal, or a combination of two of those. You will see that DARMA and other experiments using sodium iodide are actually using scintillation light only, whereas COSINUS and will do like CREST and combine a phonon and a phonon signal and a scintillation light signal. So we will use a cryogenic detector, as I've said in the beginning. And so how does this work? So basically you take your crystal and you put a thermometer, in our case a transition edge sensor, on top, and then any particle interaction in the crystal will give you a temperature signal. And what you read out is such a temperature pulse, which is in zero order. And zero order gives you the energy you deposited in your crystal. What's the nice thing about a phonon signal? Well, if you allow me this sloppy comment, everything which ends up in heat in the end. So this signal is almost independent of the type of particle and allows you to really precisely measure the deposited energy. But sodium iodide is a scintillator, so a few % of the deposited energy go into the scintillation light. And in contrast to the phonon signal, the scintillation light strongly depends on the type of particle. So by the ratio of light to phonon signal, you can do discrimination between nuclear recoils and electron recoils. And this, so to say, allows you to disentangle the modulation from the background. So starting this project, we did a simulation on what we could possibly achieve. And this is a complicated plot, so I will be slow here. What you see is simulated data in the light yield versus energy plane. So light yield is defined as the ratio of light to phonon signal. And most light is produced by electron recoils, so betas and gammas, and they have a light yield of 1 by calibration. So these are all the black events here inside the black lines, which is the beta gamma band. And then nuclear recoils produce less light, they are quenched. So we would expect recoils of sodium inside the blue band and recoils of iodine inside the green band. And DARMA, on the other hand, they measure scintillation light only. So they are measuring an energy deposition in terms of electron equivalent energy. And so where the modulation appears is between 1 and 6 keV electron equivalent. And if you plot this inside here, then you get the gray band here. And then an important thing to note is that for everything below this gray band, a scintillation light only detector with a threshold of 1 keV electron equivalent is blind because it's below threshold. And for fun, we put in a standard scenario dark matter signal here, which you see in red, and you see the nuclear recoil threshold for COSINUS with what we assume is 1 keV here, and you see we have many events, and only very few of those events make it into the gray band. So in a sense, if you read it out as a cryogenic detector, you have a lower threshold, which gives you more signal, and you have less background because you can do the discrimination between electron recoils and nuclear recoils. So what is the physics reach we might reach with such kind of a detector? This is work we did together with Felix, who's also in the audience. Basically, one has to think about the problem that with COSINUS, we first of all want to measure a rate, and DARMA measures a modulation. So how would you possibly compare those two experiments? Well, I think you can convince yourself that the modulation amplitude cannot exceed the mean rate. Or in other words, if DARMA sees a modulation, then you have to see some events in COSINUS as well, given the fact that they're using the same target. And if you do this, and I put one plot here for one mass, then you get to this plot. Okay, the x-axis is a function of the threshold we can achieve. More important is the y-axis. This shows you the bound we have to be able to set on the rate to exclude certain scenarios. And for all of this, they are halo independent. So they're independent of the dark matter halo already. And as you expect, the most easy to exclude is the standard spin independent scattering in blue. Then with a 100 kilogram day real detector, we would be able to almost exclude any falling recoil spectrum, and 100 kilogram is the goal for the very first measurement. And then if we go to 1000 kilogram days, so a magnitude more in exposure, then you can exclude any arbitrary recoil spectrum. So in conclusion, what this study shows that if we achieve basically a threshold which is lower than the one of DARMA, and we can set a bound on the rate of 0.01 events per kilogram a day, then we can exclude DARMA Libra in a model independent way that is independent of the dark matter halo. The only assumption is that the interaction is on nuclear recoils. And I think one could improve a bit on this. This was a cut and count only analysis. If you make use of the energy spectrum of what you expect, I think you can do better than that even. So in summary, with a cryogenic sodium iodide detector, you have particle identification on event by event basis via the ratio of light to phonon signal. You have a lower threshold for nuclear recoils, and you can do a model independent test of DARMA. And this is the goal of COSINUS. So we are now a collaboration with collaborators from basically Munich in Germany, Vienna in Austria and Italy. Our crystals are produced by SICAS in Shanghai and China. And okay, our last collaboration meeting, which is here in the picture, was of course also virtual. So just a time sketch. What we did in the past 3-4 years was basically prototype development for such kind of a detector. And right now we are in the final planning phase and about to start the construction for the experimental setup at LNGS. And the idea is to have by 23 the first phase called 1 pi with the aforementioned test of the nuclear recoil origin of Dharma. And then depending on what happens in the community and depending on the outcome of our measurement, one could envision a phase 2 pi and also go for an annual modulation test. But this is more the more far-term future. I will spend a bit and show you some results of the detector prototypes. So the very first prototype looked like this. So I hope I convinced you that it's beneficial to operate a cryogenic detector. So you might ask why nobody did it, because frankly speaking, sodium iodide is the last material you would use for that. One big problem is hygroscopic, so you have to handle everything in glove boxes in dry atmosphere, which you can see on the picture on the right. And another issue is that you cannot evaporate our TS temperature sensor directly on the crystal. Instead, you have to use a carrier crystal, in this case made of cadmium tungstate, and then interface it with, for example, silicon oil to the main crystal. The light detector is straightforward, conventional crest light detector. So a wafer of silicon on sapphire or pure silicon. And with this first prototype, this is data from this first prototype in the light versus energy plane. You see a linear light output. We see a phonon and a light signal. We see our calibration sources and the events at the very low light signal are events directly depositing energy in the carrier. So we were quite happy for our first test. This was very successful. And while the energy threshold was around 10 kV, the goal is 1 kV. So clearly we need to improve on that. But what was astonishing is already the light output. So almost 4% of the energy deposited in the crystal were measured in the light detector. Then we moved on with to the second prototype, which basically is already close to the final design. One main difference is that we switched from a wafer-shaped light detector to a beaker. So this looks like a cup, size of an espresso cup, roughly, made of silicon, completely surrounding the target crystal. And also this prototype worked nicely, now showing data in light yield versus energy. And again, we see the calibration sources. We even see the 3 kV potassium line a bit. And the astonishing thing of this measurement was that we measured 13% of the energy in the light detector, which is the best value for any material we ever measured, I think. So this shows you that at low temperatures, the undoped sodium iodide crystals are really a very, very good scintillator. Okay, phonon detector performance still needs to be improved. And for all these prototype tests, we were using commercial crystals with quite a high radioactivity in them. So now I could go with you through all the prototypes. So we measured already 13, and the 14th prototype will be measured next week. I will not do this, but the main areas we are focusing on is the particle discrimination capabilities and the phonon performance, so to bring the threshold down. Okay, 2 minutes. So one thing I wanted to say, particle discrimination turned out to be more tricky than we thought of, and we have an indication why this is. So what you see here is the light signal on the y-axis and an NTD signal. So we had a module with another temperature sensor, so NTD and TS. You clearly see, if you put a neutron source, you clearly see a sort of band with the NTD, and then you can look, so you identify the neutrons with the NTD, and you can look back to the TS signal. And this is plotted on the left side. So you see a neutron event in red and a beta gamma event in black. It's only a few events, that's why it's so noisy. But basically what we observed is a different pulse shape for the two, which is uncommon. We didn't observe something like that for other materials, in particular not for calcium tungstate and crest. So this is one issue. And the second issue is that the phonon signals in sodium iodide are very slow. And we think from everything we know up to now that if you manage to account for this, then both the threshold and particle discrimination can be done. So this brings me to the to-do list. So we operated it as a cryogenic detector. The light detector is performance-wise where we need this. We have clean enough crystals, and the phonon threshold we were able to bring down to 6 keV. We want to go to 1, so there's a bit work to do, and particle discrimination needs still to be verified. So, but with this, we are building up an own setup. So what we have to do is, of course, we will need more than one of these modules. In the first round, we want to install 12 of them. And then we need a shielding. So this will look similar to XENONnT, for example, where you have a water tank around your detector serving two purposes. Okay, I will speed up. So first of all, for shielding, water is good as a moderator for neutrons and good as Cherenkov muon vetor for charged particles. So in our case, will be a 7-meter water tank in height and diameter. You see the water tank on the right side, the clean room on top, and a control building next to it. And for those who are familiar, we will be the new neighbors of the XENONnT 1 ton experiment. So this is Hall B of LNGS, and you see a picture on the from the top of XENONnT to the empty space where we will build up COSINUS. Concerning the timeline, I speed up. So basically, we are starting to construct everything now. This will take us 1 year, so commissioning then should be somewhere in 2022, and then we start with 100 kilogram days, which should produce first results on dark matter in 2023. Yes, I already told that the main funding comes from INFN, Max Planck in Munich, and from HEFI in Vienna. And you can imagine we scaled up from an R&D experiment from an R&D to a real experiment. So we are always searching for new collaborators, since Fermi the cat cannot do everything. So if you are interested in joining, please just let me know. And with this, I want to conclude. Sorry for the problem with the slide and taking a bit over time. I will be available also for discussions tomorrow together with Jochen, who gives the CREST talk. We are both in COSINUS and CREST. So if you're interested, you can contact us in this Zoom link tomorrow. Thank you.
Thank you very much for this talk. Really looking forward to the results. We'll have to wait a little bit, but yes, it's one of the biggest questions that a lot of us have. So any questions from the audience? So I've seen one hand go up and down, but I don't know if that was a question. So there was Kalpana Bora wanted to ask a question.
Yes, I want to know what is the advantage of using sodium iodide as the in the detector? What's so special about it?
There's no advantage. I mean, if you look what the highest performing cryogenic detectors are, these are silicon for CDMS or germanium or calcium tungstate or sapphire for CREST. The reason why COSINUS uses sodium iodide is to use the same target material than DAMA, so that in the comparison of the two experiments, you completely get rid of any target material dependence. This is the reason of using sodium iodide.
Okay, thank you.
Thank you. There is time for one more question if anyone is. If not, then we move on to the next talk. It's another experiment. It's the PICO experiment with Eric Vazquez-Jauregui. I hope I did. Thank you very much to Florian.
Thank you. Hi, Eric Vazquez-Jauregui. Can you hear me well?
Yeah, so if you also want to turn on your camera, then people can see you in the
yes. Let me just try to find. Can you see my slides now?
Yeah, we can see the slides now.
Okay.
If you want to make them full screen, I think it's better to have them on. You should be able to do full screen now. Yes.
Okay. Perfect. Let me make this smaller and. Okay, great. I'm going to talk about the search for dark matter using bubble chambers, the work that we do in the PICO collaboration. You should see now my second slide, right? This is the PICO collaboration. We are an experiment in institutions, with institutions from Canada, the US, Spain, the Czech Republic, and India. And of course, I'm from Mexico, from the National Autonomous University of Mexico. This is a picture from our last collaboration meeting when we still could meet early March, actually, in Snow Lab in Canada. So we use bubble chambers to search for dark matter. Our target material is used to be CF3I. Now we are moving to C3F8 to have a larger response to spin-dependent interactions. This is a cartoon of our detectors. We basically have a stainless steel pressure vessel, and inside we have a quartz jar where we have a superheated fluid, in this case the C3F8. Pointing to our inner detector, to our jar, there are two cameras, and we also have a set of acoustic sensors. So basically, the operation of the chamber is that we usually start at high pressure, slightly above 200 psi. That's a compressed state. Then we relax to a lower pressure, to about 30 psi, depending on the conditions that we want to set. And that's when we have the detector in a superheated state. And then when a particle comes, interacts with the fluid, then it evaporates a small amount of material, produces a bubble, and that sets a trigger that next takes a picture of the bubbles, and then we record the acoustic signal. When that happens, then we quickly compress our detector to basically recondense the fluids, and we are operating in this cycle. We used to have two cameras in smaller chambers. Now we have 4 cameras, and depending on the size of the detector, we have about 8 to 16 acoustic sensors. You basically can make a bubble chamber with any liquid. So how does the physics work for our detectors? Well, basically the production of the bubble, it depends on the surface energy and the latent heat. And the important thing here is that it not only depends on the energy, but also on the stopping power, dE on dx. And we use usually this hot spike model that at certain threshold, that's our efficiency. It's 100%. We have refined these with experiments to basically estimate correctly what's the efficiency for the production of for the nucleation of bubbles. So this important characteristic that the bubble nucleation does not only depend on the energy, but also on dE on dx, allows to be insensitive to electrons and gammas. And that's because electrons, even if they have enough energy, they don't have enough stopping power, and they cannot produce bubbles. This is in this diagram. You can see the region where we can where we have bubble nucleations, and what we can see is that alpha decays and nuclear recoils, those do produce bubbles. But we are insensitive, as I mentioned, to electrons and gammas, and we have measured these with several experiments. This is the probability of nucleation, and this is the energy threshold. This is for the two fluids that we historically have used, the C3F8 and the CF3I. And you can see that at threshold, for example, of about 3 kVs, the 3.3 kVs actually, the probability of nucleation, this is of the order of 10 to the minus 10. That's the probability. And we have done this, as I mentioned, with our detectors and with several prototype chambers and in universities using gamma sources. So that means that our detector is sensitive to alpha decays, which consists of a nuclear recoil and about 40 micrometer alpha track. This produces one bubble. And we also have are sensitive to neutrons. These are basically nuclear recoils. The characteristic of these nuclear recoils is that the mean free path of neutrons in our fluids is about 20 centimeters, which means that we can have more than one bubble. So besides single bubbles, we can see multiple bubble interactions. And for example, in PICO 60, we used to see about a ratio of multiples to singles of 3 to 1. These are pictures of our detectors. This is about 50 kilograms of material, where you can see the jar with the fluid. This is the LED illumination, the reflections in our detector. But here you can see bubbles of produced with an ambi calibration source. So you can see here 5 bubbles in this event, and here there are 20 bubbles in this event. And we are also, of course, we expect that would be sensitive to WIMPs, also a nuclear recoil. And since this is, they have a mean free path of more than 10 to the 12 centimeters, so we will observe one bubble. One important discrimination component that we have in our detectors are the acoustic discrimination. That is the reason why we have acoustic sensors. And this is a discovery reported by the Picasso collaboration a few years ago, in which they observed that alphas are about 4 times louder than nuclear recoil bubbles. This is basically an alpha decay, which is the daughter nucleus going to moving, recoiling, and then the alpha track, the 40 micrometers alpha track, moving in the fluid and multiple radiating bubbles that in the end turn into the macroscopic bubble that we observe. And here you can see our acoustic parameter normalized, by the way, where we have 2 contributions. You see this black one, which is the one produced by neutrons. Here you can see the acoustic signal of 3 of our acoustic sensors, and they were produced with an ambi calibration source. And during our WIMP search, you can see this red these 2 peaks. We actually are able to do distinguish different alpha energies, and you can see how the power, basically the acoustic signal, is higher for the alphas. So this allows to discriminate the alpha decays. Our detectors have the following features. Our chambers are threshold detectors, so we cannot observe energy on an event-by-event basis. We also have the background suppression, the usual background suppression of dark matter detectors. They are located underground at Snow Lab. We use water shielding and a selection of clean materials. And then, as I mentioned, the background discrimination, the alphas are discriminated using the acoustic parameter. And neutrons, we have the, besides the single, we have multiple bubble events, which allow us to study if there are neutron contamination, neutron backgrounds in our detector. And to scale our detectors, we have moved from smaller chambers. These are the names of our detectors that I will briefly sketch in the following slides. So why do we use bubble chambers? Well, since we are insensitive to electromagnetic interactions, if we have a clear choice of material without any neutron contribution, we have basically a zero background detector. We can easily scale our detectors with basically the same data acquisition system, very similar, without very few modifications. We can operate at very low thresholds from a few kVs and down to EV for some fluids. And we can easily exchange targets. We can add multiple targets to our detectors. We have usually worked with fluorine and iodine, but one member of the collaboration was able to use xenon in a bubble chamber, and now some group of members from the collaboration are working on an argon bubble chamber. And the only way to measure the nuclear recoil energies is just by varying the threshold. So we are not sensitive to the nuclear recoil direction. Also, in this slide, I just would like to emphasize the reason why we use fluorine. What you can basically here see is basically the effective field theory couplings, the response type for the different elements. Here you can see the standard spin independent, and these two are the spin dependent, the longitudinal and transverse components. And you can see that in the case of the coupling to the proton, fluorine is the best material due to this unpaired proton in the nucleus. So it has the largest response for coupling to protons. So we can also, as I mentioned, study with other materials, with other targets like iodine, bromine, xenon, and argon. We can go to high A targets. And of course, if we use a chamber with hydrogen, we could enhance the sensitivity to low mass particles, and this has been tested in prototype chambers in one of our institutions. This is the family of our detectors. Basically, we started with the Q4, and it started after running at Fermilab. Then it moved to SNOWLab in 2010. This was a 2-liter CF3I chamber. Then we scaled up this detector to a 40-liter chamber that was called Q60, which is this one. These are 2 liters, about 4 kilograms, and these are 40 liters. We also, in parallel to Q60, we also developed PICO 2L for a C3F8 chamber, which you can see here, and then PICO 60. Now, due to some backgrounds, unexpected backgrounds that we were observing in our detector, we flipped our detectors. It seems that we were operating them upside down. And as you can see, this chamber is in this position with the acoustic sensors here. In all these 4 detectors, this one is just basically what we call the right side up chamber. This is a commissioning detector that this is a picture from actually just before the lockdown. This is the first event that we observed, and we are currently commissioning the detector. And then PICO 500, which will be our future ton scale experiment, expecting to go live in 2021. Our detectors are located at SNOWLab, 2 kilometers underground near Sudbury, Ontario. And then you can see here 2 kilometers, the shaft, and then about a mile into where the lab is. The physics program at SNOWLab is focused on neutrino physics and dark matter searches. This is the snow cavern, and these are the relatively new areas post snow. And we have detectors located in this area. We have PICO 40L now, and we used to have PICO Q4 in this area. And in the cube hole, this is where PICO 500 will be located. And as you know, SNOWLab is the home of the snow experiment. This is the work that the limits. In this slide, I show the limits that we have basically obtained over the last years. This is the spin-dependent WIMP proton or neutron, 90% confidence level cross sections. And you can see how the Picasso collaboration start to lower the limits. Then we had the PICO 2L and PICO 60 detectors. And now we are about to turn on PICO 40L, and we expect that PICO 500, this will be our tone scale detector. We have to move this about 1 year as we made this in 2019. These are some pictures of our detectors. This is basically the synthetic quartz jar where the superheated fluid is. These are the acoustic sensors in this chamber. They were located on these sides of the detector, and they go inside of this pressure vessel. Here I have other few pictures. This is the pressure vessel inside of the water shielding tank. As you can see here, the day that we put our chamber inside of the pressure vessel, this was PICO 60, already more than 6 years ago that this happened, actually 8 years, I think. And this is the pressure vessel with the viewports for the cameras. And this, you can see here the LED illumination of the detector. So I want now to present some of the results from PICO 60. This run took place from November 2016 to January 2017 for the first physics run. These were 30 days lifetime. Our detector was filled with 52 kilograms of C3F8, and we collected basically 1,167 kilogram days of dark matter search data at a threshold of 3.3 keV. So one of the issues that we had earlier detectors was an unexpected background produced by particulates, quartz and steel. And for these, we cleaned our detector and did an active filtration, had an active filtration system to remove these particulates. And I want to present the result of a blind, actually it was a deaf analysis because we basically removed the acoustic parameter from our analysis. We observed 3 multiple bubbles observed, consistent with our Monte Carlo background expectation. These are the results. Basically, the fiducial mass was 45.7 kilograms. And after the selection cuts, we observed 106 events. Here you can see the distribution of the events in the jar set versus how they are observed, how they are distributed. And then this is the acoustic parameter. And you can see in black our neutron calibration data. And then on red, you can see these 106 events. And that's because after unmasking, we observed no nuclear recoil candidates. So all these 106 were consistent with alpha decays. After that, also in 2017, we did a complete, longer exposure, even a lower threshold. And for that, we also modified our analysis. We basically increased the fiducial mass. And that's because we basically had a better discrimination of events in the walls of the jar. And we ran our detector at 2.45 keV. So we observed 3 single bubble events in this dark matter search. And one of the changes is that we increased we had a wider AP acceptance region, and this is the same acoustic parameter, where you can see the neutron and gamma and the neutron calibration data, and in red the WIMP search data. These are the results that we currently have with our detectors. These small plots are from the first physics run, and these are from the complete exposure. So as you see, the blue one is what we have at a threshold of 3.3, and then this one is the complete exposure, including the 2.45. And basically, PICO is leading the spin-dependent WIMP proton cross-sections, and at low regions, even better constraints that indirect detection experiments, such as IceCube. And for the spin independent, you can see our limits in blue also from the first physics run, and then from the complete exposure. And they were published in 2019. To also correctly assess, present our limits, we discussed with the LHC dark matter working group. We came with, they came with a set of recommendations where we presented our results in terms of 4 free parameters that included their dark matter mass, the mediator mass, and the couplings, the coupling to dark matter and the coupling to quarks. And here you can see the WIMP mass and the mediator mass, and you can see how the results of CMS compared to the results of PICO 60 from the first physics run for a couple of parameters or values for the coupling to quarks and dark matter. So next, we are basically commissioning PICO 40L. As I mentioned, this we just flipped up. This is the right side up chamber, as we call it. We want to demonstrate the background reduction and technology improvements for PICO 500. We are focusing on reducing the neutron background that we observe in PICO 60 and confirm that this design works on a large scale since it has been proved only in prototype chambers. From the science point of view, these are the limits from PICO 60, and we want to improve by 1 order of magnitude with PICO 40L. And these are pictures of the commissioning of the new detector. This is our chamber. This is the quartz jar. This is a pressure vessel in the same tank of PICO 60. And this is our detector. You can see here the first bubble. So this technology actually works. We are observing events, and we are expecting to go live by the fall. And PICO 500, this is basically, we are designing this detector. We are we have funding secured for the construction of this detector, and this is basically the water tank where it will go, located in the cube hall at SNOWLAB. And as you can see, we will lower even 1 more order of magnitude compared to PICO 40L. And you can see here a comparison between LZ, the coupling to neutrons, and also the neutrino floor that it is lower for us for C3F8. So that's basically the future of our detectors. This is our detector, the one that I just presented the results during the installation in 2016. And now I'd like to move to my conclusions. So basically, the PICO bubble chambers are producing world-leading limits, and we mostly have been using fluorine targets. Our results from PICO 60 showed factor 17 improvement on the proton constraints, WIMP proton constraints. And last year we published our full exposure at a lower threshold of up to 2.45 kV. We have our backgrounds, these unexpected backgrounds under control. And we are expecting that PICO 40L, the right side of chamber, will come online this fall. We are just commissioning our detector. And the design of PICO 500 is very advanced. We're about to begin to the installation next year, and begin the construction next year. So I'd like to finish saying that, well, stay tuned for the new leading results from the PICO experiment. Thank you.
Thank you very much for the nice talk. It's well, coming from a collider perspective, especially nice to see that there is also putting direct detection results on collider-like planes. It's interesting to see that perspective. It's not often that we see that. Are there any questions? It doesn't look like it, so I will possibly ask one myself. If you...
Yep, of course.
So I was wondering what kind of statistical analysis you use for the setting the constraints. And I understand if you're more of a detector expert rather than a statistical analysis expert, and this is not an easy question. But I was curious.
Yes.
Different things done, different
experiments.
So
to get our limits, we use Feldman cosines. So
Mm-hmm.
basically, that's what the limits are usually obtained.
Because you mentioned some even some machine learning and advanced data analysis techniques, I was wondering.
Okay.
What is the gets you from?
Yes.
Having
I thought you were asking me only about how we set the limits.
Well, it's how you get there, combine all the ingredients. That's what I'm curious about.
Yes. So basically, what we do is using the pressure sensors and image reconstruction. We basically remove events from the walls of the detector, and then in this physics run, we also use a neural network score to basically separate the nuclear recoils, the neutron nuclear recoils from the WIMP search. This one in black here correspond to multiple bubble events. So that's basically how we, in a general way, using the acoustic parameter, the image reconstruction, and the pressure sensor, that's how we obtain this WIMP selection efficiency. So that's basically what goes into a very general receipt of what we what the analysis we do. And yes, you observe here that we use this neural network score, and this was just to confirm our usual analysis, because usually what we do from this acoustic parameter, we obtain its Fourier transform, and then we separate in bands to select the best discrimination between the nuclear recoils and the alpha tracks. So in addition, that you can see here in this acoustic parameter. In addition to this, for this physics run, we included this neural network analysis. And then from that, we basically, as I mentioned, we did a blind depth analysis, and that's when we have our candidates. And then after unmasking, we basically, in this case, we observed that we only had alpha decays.
And what would you have done if you had found a candidate?
Well, that depends on the expectation of neutron backgrounds that we have, right? So we have only actually in the complete exposure, we observed 3 single bubble events that were consistent with our background expectation from neutrons. That's what we want to actually reduce in PICO 40L. So these were single bubble events. So these were candidates or consistent with our Monte Carlo expectations. Of course, if we don't, if we see one event that is not consistent, well, there's analysis that we have to do. Of course, only one event. It's just a very small number, right? But in this case, these events are consistent with our Monte Carlo expectation.
Thank you. We have another question, but I think at this point we can also release people to go and get coffees, but we can keep discussing during the coffee breaks there for that.
Okay.
And we'll resume the session at 11, but Kalpana Bora has a question. So.
Yes, hi, thank you for the nice talk. So I have a very simple question. What kind of dark matter candidates can be detected in these detectors? And number 2 is in what mass range?
Okay, we look for the WIMPs in our detectors. Let me, here are the plots. So this is a WIMP search detector. And in the case of spin dependent, we basically go from about a few GeVs to maybe 1 TeV. So that's the range of the dark matter candidates that we are searching. So basically, this is due to the nuclear recoils, the kinematics, of course, in the nuclear of the nuclear recoils, and that's the range that we are sensitive. For spin independent, it's basically the same. So we are just focusing here in the low mass range. As you can see, this goes from 1 to 10, and that's because our detector is sensitive to these interactions in the majority due to the low threshold at which we operate. But of course, this also extends as this in this plot. So usually this is a typical range, right, for WIMP detectors, few GeV up to 1 TeV.
Okay, thank you so much. Thank you.
Thanks a lot. So now it's official coffee break, but there's always Mattermost for more questions.
I'm going to stop sharing. And
thank you very much. Thanks for the talk again.
Okay, let us resume the dark matter session with the third block of talks. The first talk is by Andrey Alexandrov about the NEWSdm experiment. Andrey, whenever you're ready, please share your screen.
Yes. Okay, can you see the slide?
Yeah, that looks good.
Okay. Sorry. Okay, can you hear me now better, I suppose? So, greetings to everybody. I will report about a relatively young experiment, which is called NEWS. It is now in a phase, transition phase from an R&D to a real experiment, and if it happens, it will become the first directional dark matter detection experiment that uses a solid-state target. So first few words about the collaboration. It unites 75 physicists from 14 institutions in 5 countries. And below you can see the website of the experiment and also its letter of intent. So I invite you to check out and if you are interested to get more information. So this is a quite famous slide about the motivation, why the directional detection is important. It happens because the directional information cannot be associated with any known terrestrial background. The motion of solar system inside dark matter halo would make it appear as dark matter particles come from a very specific direction, which is Cygnus constellation, and a detector placed on Earth laboratory will see it as a kind of wind of particles. So, and the idea is to reconstruct the direction of recurring nuclei. It is also important because probably it is the only possibility to perform measurements below the so-called neutrino floor, where the coherent neutrino background, coherent neutrino scattering represents an irreducible background. So, and nuclear motion gives a very good opportunity to build a scalable detector, scalable to large masses. So the I forgot to say that NEWSdm stands for Nuclear Motion WIMP Search with Directional Measurement, and its idea is to use nuclear motion to detect nuclear recoils. Nuclear motion are supposed to be fixed with respect to the Cygnus constellation, and therefore the detector will be placed on an equatorial telescope, and that in this case dark matter particles will arrive always from one direction and will be accumulated inside the nuclear motion. And of course, it will be placed in underground laboratory to reduce external backgrounds. It will be placed in the LNGS in Gran Sasso laboratory. Okay, now about the principle how nuclear motion can detect a charged particle. So it composed of silver bromide crystals. Above you can see its images in electronic microscope. So charged particle passing through this crystal ionizes it, and then electrons start migrate inside crystal until they are trapped by a lattice defect on the surface of the crystal. the set of electrons create a local field and attract interstitial silver ions, which arrive there, recombine with the electrons, and create a cluster of metallic silver, which is called a latent image. This image can be stored, is persistent, can be for a very long time until the emulsion is not developed. Development is a chemical process that amplifies this small cluster of few atoms of metallic silver. First, a filament starts growing on its place, then it is growing until the development process is stopped. After that, all remaining crystals are dissolved, and in emulsion what is remaining is emulsion is silver grain in form of filament of very undefined shape. So after that, this emulsion is inspected in optical microscope, and we see an image like this in a microscope. So of course, being a solid state target, we expect that nuclear recoils will be very short. In fact, this simulation shows that even for 100 GeV WIMP mass, recoil length will not exceed 1 micron. And this poses a significant challenge if we want to use optical microscope. First of all, we want to use them for their speed, since if we want to process large amounts of emulsions, tons of emulsions, it seems to be the only choice. But the disadvantage is that due to diffraction limit, the tracks which are actually two or more grains placed very closely cannot be resolved in the range below 200 nanometers, and the major part of events are located exactly here. So to illustrate this, I can show you several images. That below you can see an X-ray image of a track, which the length 380 nanometers, and above is the same tracks in optical microscope. Okay, here there are two tracks made of 2 grains, but the distance between them is still larger than the resolution, and that's why in optical image we actually can resolve them even by eye. But everything changes when we go below 200 nanometers, where we just see one single peak. Maybe in this case it is slightly asymmetrical, but if we continue to decrease the length, it will become perfectly spherical. So in this case, we need to change the approach. We need to pass to super resolution. And our collaboration has developed a new technique, which is based on plasmon resonance effect, which happens when a metallic nanoparticle or grain is being illuminated by a wavelength of light. Light is actually an electromagnetic wave, and acting as an external force, it makes the electronic cloud in conductive band of this nanoparticle to oscillate. And when the wavelength, the frequency of illuminating light coincides with the internal frequency of a nanoparticle, its resonance conditions occur, and this makes to grow the scattering cross-section of this nanoparticle, so it just becomes much brighter. This effect is also dependent on not only on composition, but also on size and on shape of a nanoparticle. in study. So, for example, if nanoparticle is not symmetric as shown in bottom right plot, so if we radiate it with an electromagnetic wave where with polarization okay, like this, the resonance condition occurs at wavelength lambda 1, and if we change the polarization of the light, it will happen on another wavelength lambda 2. And if the optical system uses for illumination, for example, monochromatic light with wavelength tuned to lambda 2, it will make that the microscope will see particle at certain polarization and will not see it on other polarization. So it can be thought about like a switch. So we can selectively switch on and off nanoparticles. So how can it help us? So this is the initial configuration when we don't use polarization. In this case, the two close nanoparticle will both visible and only one peak appears, so we cannot resolve them. If we introduce only one polarization and start to changing its angle, then at some point we will see only one nanoparticle. It will be dominated in brightest distribution, and the other one will be suppressed. Then, if we continue to change, we can come to the opposite position, and analyzing brightness distribution, it becomes possible to understand the underlying configuration, what caused this change. So to demonstrate this, we have built this microscope, which actually uses light illumination at 460 nanometer wavelength. It works in reflected light, so collects light reflected from the sample, and then the polarization spectrum is analyzed with the use of a liquid crystal polarization rotator and the polarizer plate. The use liquid crystal is quite important since it's not mechanical and doesn't introduce mechanical vibrations, which makes us able to measure point, the coordinate of a point within a field of view with the accuracy of 6 nanometers. So what happens if we have a look at two close nanoparticles? So without polarizer, we see just a spot, and after we start rotating the polarizer, we see that this spot starts moving. No, it's not a mechanical movement, it's an optical effect. So, but this effect allows us to make the following analysis. So we measure the center, the trajectory of the center of this spot, plotting them on and the plots below. When the coordinate of each point is known with accuracy about 6 nanometers, and we see that the barycenter has moved about 100 nanometers. We call this value as barycenter shift. So barycenter shift in this case is about 100 nanometers, and we also can measure its direction of the barycenter shift, which in this case perfectly coincides with the beam direction. This is 100 keV carbon ions in emulsion. Okay, then we did the following following test. So we irradiated emulsion with carbon ions 100 keV with energy 60 keV, 30 keV, and also to test 10 keV with the vertical radiation. These 3 were horizontal radiations, and 10 keV were vertical perpendicular to emulsion surface. And we have divided all the events in 2 populations. One of them which are called moving is with barycenter shift larger than 20 nanometers and static barycenter shift smaller than 20 nanometers. And we see that these moving events, they have some direction. They are anisotropic, while the second population is almost perfectly flat. And the direction of anisotropy coincides with the known beam direction, which was at 0 degrees. This difference with beam direction plotted. So we have stated we can sensitive to direction up for the energies down to 300 keV. Okay. The same analysis can be done also in 3 dimensions, and our collaboration has patented a microscope that is capable of doing that. It makes this analysis in 2 planes. One plane is a horizontal one, and another plane is vertical one. And applying this analysis in two planes, it becomes possible to make a full 3-dimensional reconstruction of the event. Then the previous analysis was done in monochromatic light, but if we use white light or wavelengths and start changing polarization, in this case we can trace how the resonant wavelength changes. So in this case, as you can see, there are 2 nanorods, 45 by 80 nanometers and 45 by 100 nanometers, and they have different responses. One changes from blue to green, another one changes from orange to red to blue. And this depends on, so we have also information about the sizes of nanoparticle. And this can be important because size of grain is connected with the energy deposition, which is done, produced by a recoiling atom. To demonstrate it, we can see this alpha particle track, which when it stops produces very red and very large and bright grain. That means that in that point there was a big energy deposition, and the same we are now, the same approach we are now trying developing to the application to carbon ions, to recoils, which, as you can see, it changes from orange to green, and in this way we expect to get also the verse of the nanoparticle of a recoiling track. So we can do 3-dimensional reconstruction and probably also head-tail discrimination. And plasma analysis allows us not only to perform reconstruction of event, but also to perform background rejections. The fact that there are different processes that can activate the crystal. It can be nuclear recoil, it can be electron recoil, it can be also some thermal activation. They produce slightly different grains. And with the means of machine learning, it becomes possible to distinguish between them. For example, we have created two networks and trained them by using something that will look like signal. They are carbon ions with different energies, and we train them to distinguish between signal and background, which in this case will be gamma emulsion irradiated with the gamma rays, and also populated with the spurious, spuriously activated grain, which we call fog. The first network takes only color images with all polarizations, and the second network took polarization taken with the monochromatic light, and as we can see, the level of 10 to 2, 10 to 3 can be achieved with the machine learning approach. Then, okay, this slide summarizes the backgrounds, expected backgrounds in our experiment. As for intrinsic background, radiogenic neutrons are not problem up to masses about 10 kilograms. Intrinsic backgrounds are mainly due to carbon-14, since gelatin is an organic material, so it is a natural process. External background, they can be reduced by an appropriate shielding, and the dominating cosmogenic neutrons, but for 10 kilograms, they are still few. And we have quite many leverages to reduce carbon and gamma, to reduce beta and gamma background. So we are first of all, that emulsions, they are not sensitive to the factor 10 to the -3 to electrons, but they are sensitive to nuclear recoils. We also can go to cryogenic temperatures and get other 4 orders of magnitude. And as I have shown before, there are polarized light and wavelength analysis cover. But the final goal are the R&Ds that are now performed in Japan is to replace organic gelatin with synthetic polymers, which will not be radioactive. So we have also installed underground emulsion production facility. We can produce emulsion ourselves in low radioactivity environment and put it directly into the detector. And this fall is planned 10-gram demonstrator run. Everything is ready. Actually, it was ready already in spring, but due to lockdown, it was everything was moved to autumn. And then we started to prepare a 10-kilogram scale detector. Here is the sketch. So there will be a polyethylene shielding, cryogenic device, and also equatorial telescope. So with 10-kilogram scale detector, we plan to explore partially a gamma region, and if we manage to improve our detection threshold to 15 nanometers, we can explore the full gamma region. This is this last slide before the conclusion, that in future, of course, the directionality becomes useful only below the neutrino floor. So to reach this, we will need several tons detector. Actually, we need at least 10 ton, and we also will need to reduce detection threshold down to 30 nanometers. It can be done with by producing emulsions with smaller grains. So technologically, it's possible. And then. So here's the conclusion. So new nano-emulsion grain experiment is under development, and we have made several technological breakthroughs to achieve two-dimensional and three-dimensional super resolution, heterodiscrimination, discrimination, and also cover analysis. We use machine learning to handle image data complexity and for background separation. We have installed new production machine. This fall we will do a demonstrator test, and after that we will be ready to our future goals. So we are planning to make a 10-kilogram scale detector, and TDR is under preparation. So thank you very much for attention, and for further questions after these 5 minutes, I invite you to use this Zoom meeting ID or write me directly, give an email. Thank you very much.
Thanks a lot, Andrey. So other questions or comments? So I wait for raised hands. I asked in the meantime, as a former member of Opera, how long does it take for you to scan a 100-kilogram untriggered block of emulsion?
We are planning to use it in several steps. The first step will be just a volume scan. So scan everything at very fast microscopes. They are next generation, not like an Opera. Now we can scan at least one order of magnitude faster. And the first scan will produce predictions. Then with the high resolution microscopes, we go to check those predictions one by one. And this way we can combine the speed with low resolution and high resolution. So the time, actually, 10 kilogram, we plan to scan in several months.
Okay, impressive. Thank you. Okay, and we have one question from Kalpana. Please go ahead.
Yeah, hi. I want to know how, about this plasmon resonance effect. How is it being utilized here? Plasmon resonance effect.
Could you repeat the last part of the question?
How the plasmon resonance effect is being used here in this detector?
Well, the idea is that when the wavelength of external light coincides with the intrinsic, with the plasmon resonance wavelength, the scattering cross-section of exactly this nanoparticle changes, it increases. So the nanoparticle becomes brighter. So it can happen that you couldn't see it, but then suddenly you can see it. And we use it in order to selectively switch on and switch to introduce some changes in brightness distribution. By changing the, we scan all possible polarizations with the microscope, and then we go to, for example, to an event and see how brightness distribution changes for this event. So, for example, as shown, as shown here, in configuration there are two grains, but we don't see them. But changing the polarization angle, we can see that one grain becomes brighter. Then as we continue change, it becomes dimmer, and the other one becomes brighter. And this makes this spot, which was initially static, to oscillate. So it's a dynamical change of brightness distribution. And analyzing this, okay, this is very primitive analysis. We're developing more sophisticated one, but by analyzing the distance at which it displaces, it is possible to understand the direction. But by the fact that it's oscillating, it's possible to understand that there are at least two grains, and that it happens, it's possible to understand that there are metallic particles, silver particles. Otherwise, it could be, for example, dust, but dust doesn't exhibit plasmon resonance.
Mm-hmm. Okay, thank you so much. Thank you.
Thanks a lot.
Okay, now we have the next talk.
Okay, thank you.
You are muted, Katarina.
Thank you. Yeah, didn't unmute. So we have the next talk now. It's another direct detection experiment, the PandaX experiment, and the talk is given by Ning Zhou. So if you can try and make it full screen and switch the slides, that works. Thank you. You can also turn on your camera if you'd like, so that we see you.
I've already done that. So can you see
perfect.
that?
Yeah. Now
okay.
We can see you. Great.
Okay, great. Thanks. So today I will present the latest results and the status of our PandaX experiment. So my talk will cover the WIMP search results with the PandaX 2 full exposure data, that is 132 time day. And then there is interesting preliminary results about the Axion search from the low energy electron recoil events. And the end, I will give an overview of the current status of our next generation PandaX photon experiment. So our experiment started in 2009, and up to now there are around 50 scientists in the physicists in this collaboration. So this experiment is located in China Jinping underground laboratory. That is the deepest underground laboratory in the world at horizontal access. So this laboratory has been upgraded to the second phase with larger and more experimental halls, and our future experiments will be run in this B2 hall. And this laboratory facility construction has officially started since last summer. And our detector is similar to xenon. One ton is a dual phase xenon TPC. It can collect the scintillation light and ionized electrons from the scattering of incoming dark matter with target xenon. And based on these two signals, we can reconstruct the scattering position, and also it provides a good discriminator for electron recoil and nuclear recoil events. So the PandaX 2 is has successfully completed last summer, and the total exposure is 132 time day. And the first 54 time day result has been published, and we have the new data. Throughout the data taken, we have formed many calibration runs. For instance, right after run 9, there was tritium injection, but this residual tritium became one of a significant background in the following runs unexpectedly. So in the full data analysis, there are many improvements. So we have the new positional reconstruction, and we have new detector response model, and also the dominant backgrounds have been evaluated in the more robust approach. So during the data taken, we noted that some of the 7 PMTs became unstable gradually due to the after pulsing, etc., and noises, etc. There are 5 in the top and 2 in the bottoms. So in the new full data processing, we decided to turn off these 7 malfunctioned PMTs, but the consequence is that they will distort the positional reconstruction, especially around these PMTs. Therefore, we developed a new positional reconstruction algorithm that's based on the optical simulation of the detector, and which take into account this turned off the PMTs. So this algorithm is trained with Krypton 83 isomer calibration events, which are evenly distributed inside the detector. So the improvement is significant, as can be seen from these plots. The left is the older reconstruction algorithm. We still see some structures for the PMT structures of the PMTs. So the new algorithm did make the reconstruct evenly distributed Krypton events as expected. Okay. To understand the detector response to low energy events, we have the tritium and radium calibration for the electron recoil, and MB for the nuclear recoil events with more statistics. So we developed a new detector response model based on NEWSdm 2.0. But the parameters are fitted to the data. So from the bottom 3 plots, this is the energy spectrum of different calibration source. We see that our model is able to describe this spectrum pretty well with after implementing this data quality cut efficiency. Okay, and another improvement is on this background estimation. So here is a summary of the main background in the detector. So the xenon 127, that's due to the exposure to the cosmic ray on ground, but the lifetime of this isotope is short, so that in run 11 it decays away fully. And the tritium that is introduced after run 9, we fit it from data directly, so I will describe that later. For the radon background, we notice there is some depletion effect that have to be measured from the calibration detector as well. So for the krypton 85, it's not constant throughout the data taken. It's simply due to the air leakage. So for the neutron or the surface events, we have the newly derived data-driven approaches. And also for the accidental events, we have newly trained PDT discriminator to spread them further. So for instance, I just take several for instance. So for the radon background, the major the contribution is actually from the radon daughter. This led 214, and but its concentration in the xenon, its radioactivity is now equivalent to the other daughters along this line, along this decay chain. The reason is like this. So the radon progenes are charged particles. So they are attracted to the cathode in the detector, which apply the negative high voltage. Therefore, the concentration of the radon daughters in this detector is not uniform. So along this decay chain, the concentration in the fiducial volume or in the center of the detector becomes less and less, since some of them are attracted to the cathode. This we call the depletion effect. So in order to estimate this lead 214 level precisely, we have a new method. We just try to do the interpretation from this earlier daughter, polonium 218, and the later daughter, bismuth 214. And the ratio or the depletion effect between these two isotopes, between these two daughters must be measured directly from data. That's we have this radon calibration, which was performed in the end of the run. So this plots show what we got from the data. We see that the activity of different daughters are quite different. So we use this ratio to get the right estimation of the lead 214. So eventually we got this 10 microbecquerel per kilogram for this lead 214 radioactivity. So the another background, the important background, the surface events. They are mostly the electron recoil events from the radon played out from the surface of the detector itself. But when the ionized electrons drift towards upward to the gas region, some of the electrons got lost to the surface. So the consequence is that the surface events, even though the electron recoil, the distribution shifted down below the ER region, and the leakage to the neutron nuclear recoil region is non-negligible. That's our WIMP search signal region. So we have a data-driven approach to estimate this contribution. So that is just do the extrapolation from the outside fiducial volume, and the fitting function is given by derived in this large S1 control region. Okay, so another important background is a neutron background. That's exactly the same as the WIMP signal. So we derived a new method. Since in the calibration, we found that the neutron events can be associated with high energy gammas due to this neutron capture, etc. So from this high energy gamma control region, we can extrapolate to this low energy signal region. So the extrapolation scale factor can be calculated from Monte Carlo simulation with this effect included. So this method has been tested successfully in the MB calibration data, and then is applied in our dark matter runs. And eventually we found that there are 3 ± 1.5 neutron events in our signal region. Okay, so given this improvement, we have a better control of our background. So this is a summary of the background budget in the low energy region. Compared with the previous published data, the RON 11 have more backgrounds. One reason is due to the air leakage during the data taken. So the krypton contribution is almost doubled. And also the residual tritium contribution, that is one of the dominant after around 10. Okay. So then we perform this WIMP search. Just for this new data, RON 11, we did the blinded analysis. The signal region is the same as before. So the total, we have 1,220 events with 38 below the nuclear recoil medium region. So that's consistent with our background expectation, which can be seen from this table. So we derived before performing the statistic testing, we demonstrate the distribution of these events with high WIMP hypothesis likelihood. So there are 3 events in RON 9 and 7 events in RON 11. So the likelihood from different sources of these 10 events can be seen from this plot. So the distribution is showing here. So that in the top are the position distribution, and the bottom is the S1 and S2 distributions. So from this one, from this plot, we can see that a large fraction of these 10 events are located very close to the edge of our fiducial volume selection. So, and they also have a very large, relatively large S1 signal. So that indicates that these events can have a non-small, can have large probability to be from the background sources. Okay, so here is our limits from this full exposure data. So that's showing in this red solid curve. As compared with our previous results, the blue one, so the expected sensitivity is improved indeed, but there is no lower 1 sigma lower fluctuation as before in this full data. So this results will be submitted to journal tomorrow. We will find more details later. Okay, so in the WIMP search, this low energy electron recoil events are the background, is the one we want to suppress. But it's a signal region for the Axion search. This is a very hot topic, just due to the recent observed access in XENONnT 1-ton experiment. So we we are currently performing the analysis on these low energy events, ER events. So compared with the WIMP search region, we expand the energy window to 25 keV and reduce the fiducial volume to 250 kilogram. So in this way, we are able to reduce the surface background to a negative level, and the expanded signal, the energy window can help to control the background evaluation. So for these dominant backgrounds like xenon 127, krypton, radon, and tritium, we rely on the spectrum fitting to data directly. So it's critical, therefore it's critical to have a solid background model for this spectrum. The good thing that we have calibration data to control them. For instance, for the tritium, we injected tritium twice in our detector, and one is right after round 9, the other is in the end of the round. These two periods are separated by almost 3 years, but the energy spectrum from this calibrated data agree pretty well, and also our background model can describe that pretty well. And the flat electron recall spectrum is estimated from the radon calibration, as shown in the bottom plot. And of course, there are several systematic uncertainties to be considered that include these data response model parameters, and also the non-linearity of data taken baseline suppression, and also, of course, the theoretical uncertainties for this beta decay. And with this spectrum, we need to estimate we can estimate the background, the contribution. So the interesting part is for the tritium, since it's peaked at the low energy, but there is no direct measurement of this background. So we have to rely on the spectrum fitting. So we performed the unbinned likelihood fit on these 3 rounds, with the tritium contribution floating independently. So the right plot, this plot shows the fitted results, and the orange histogram is the best fit tritium in each data set. So the resulting tritium level is consistent with very close to each other. So that's consistent with constant tritium rate through in our detector. Okay, so that we fit the data energy spectrum for all the data sets simultaneously. In total, we have 2,200 events. The estimated background is consistent with the data with 1 sigma. The fitted spectrum is showing in these plots, and the fit quality is reasonable. Then we perform another fit. That's the background plus signal fit. So with the tritium axion contribution, both these contributions floating. Since their shapes are very similar to each other, so the degeneracy between these two contributions in the fit is unavoidable. So the fit result is showing here, and we didn't see significant best fit signal yield. And the fitting quality, the chi-square, is similar to that in the background fit. That indicates that that indicates limited sensitivity from our data. So this analysis is still work in progress. Okay, that's for the PandaX 2. Now we are moving to the PandaX photon in this new experiment hall. In this new hall, we have built a big ultra pure water tank for the children. from the laboratory, from radioactivities of the laboratory itself. And this detector will be put inside this water tank. It's also a dual phase xenon time production chamber with the photon in the liquid xenon in a sensitive volume, and the 3-inch PMT in the top and the bottom to collect the signal, and the 1-inch PMTs surrounding the detector, serving as a veto system. So with the 6-ton-year exposure, we expect to have 10 more sensitivity than the current PandaX 2. And for this low energy ER region, with 1-ton-year exposure, we could have definitive test on this Xenon 1-ton result. Okay, the PandaX photon is still under construction, and the pandemic caused some delay, and we are trying best to catch up. Okay, here is summary. So the PandaX 2 has completed successfully, and we are working on the PandaX photon now. So we hope the commissioning of the PandaX photon can start in the end of 2020, and stay tuned. And the more exciting time will come. Thank you for your attention.
Thank you very much. That was a very interesting talk, and it's nice to see all the progress from PandaX, and that there will be also a test of the excess.
Yeah.
So I'm sure a lot of people are looking for that. And are there any questions about the talk in general? Maybe a last one then. So in case you do confirm the excess of xenon 1 ton, what does that tell us?
Yeah, that's interesting. Since the excess currently is in tension with the theoretical or some cosmology measurement observations. So at this moment, there are still some other models like neutrino magnetic moment, etc. So we will see.
Alex Elykov has a question now.
Yeah. Hi. Nice talk.
Hi.
I have a question actually, not about the excess, but about your slide with the event distributions that you showed for the WIMP analysis. This one, yes. So for run 11 for the 80.3 ton day, so maybe I missed it, but what exactly is the background shape? And okay, so 1,000 centimeters and in radius, why the shape is so box-like rather than, I assume it's ER, right? Or what? Basically, the question: why the distribution is not more homogeneous in that? Like there's a population that are on 1,000 centimeters, which is basically a lump of events.
You mean this region?
Exactly. Why? So this is what exactly is, and why it's not distributed more homogeneously in Z in the time.
Actually, there is leakage. There are leakage during the run 11, and also the running condition is different from before. So the different high voltage and the surface background is different as well.
So this is surface background.
Yeah, that's.
Mm-hmm. All right, thank you.
Mm-hmm.
Thanks. Any more questions on this talk? I don't see any, so we can move on to the next one.
Okay, thanks.
Okay, and then we move to the next and the last talk of this session, which is a report on the CDEX experiment from Hau-Bin Lee. Whenever you're ready,
okay.
Please share your screen.
Yes. I will share my screen. Okay. Can you hear me?
I can hear you. I cannot see you. If you have a camera, please switch it on as well.
I don't have a camera, sorry.
Okay. Okay.
So I will just share my screen. Okay.
Okay.
Okay. Okay. I'm going to give a brief report of the annual modulation result from the CDEX experiment. I will introduce the CDEX 1B experiment, and particularly on the data quality analysis, and then I will discuss about the result on the annual modulation, and then at the end I will discuss about the Midal effect. Okay, I think most of us knows this. Basically, the annual modulation is looking at the spectrum different between June and December due to the Earth rotation. At this June, the WIMP velocity will reach its maximum, and then at the December, the average WIMP velocity will at its lowest point. So what we are looking at is looking at the different. Showing here is a typical 10 GeV WIMP Lecoy spectrum on the germanium from the Halo model. So these two curves is the spectrum from different date, and what we are trying to looking at is the difference of the spectrum, which is showing here. So the requirement for this type of analysis is that we need to have a long and stable experiment running. So let me explain more. Compared with a typical time integrate analysis, is that the time integrate analysis is looking for the SS count. Now, for the annual modulation, we are looking at the difference of the count between June and December. And the problem with the time integration and for a typical germanium experiment is that we need a lot of energy spectrum modeling to understand the background and then to do the background subtraction. However, with the annual modulation analysis, this type of confusion can be ignored most of the time. And the other thing is that the best sensitivity of the time integral analysis is always as the lowest energy bin, which is also usually with the largest uncertainty. And however, for annual modulation analysis, as you can see here, the most sensitivity bin is not at the lowest energy. So that means when we look at this signal, the most sensitivity bin is not the largest. It's not with the largest statistics uncertainty. So next, I will going to explain about the CJPL. I think the last talk has explained a lot, so I will briefing here. So the experiment is located at the CJPL lab, which is at the Sichuan at this Jinping mountain. There's a tunnel here. So the lab is located at the middle of the tunnel. The overburden rock, there's an overburden of 2.4 kilometers of rock, making this position the deepest among the underground experiment lab. So this is a layout of the CJPL phase 1 experiment. So the CDEX experiment is located here at the bottom of the tunnel. So in this talk, I will base on the data from the CDEX 1B. CDEX-1B is a improved version from the prototype CDEX-1A experiment. The difference is that the CDEX-1A, the threshold of the CDEX-1A is roughly 500 eV, and in CDEX-1B, due to the electronics and design improvement, the threshold can reach as low as 160 EV. So this allows us to look at the very low recoil energy. So for both experiments, a typical shielding and detector configuration will, as showing here, usually it is surrounded by a NEI detector as an anti-compton detector, and also the germanium is here, and also it is always surrounded by a copper shielding. So showing here is when both CDEX-1A and CDEX-1B run parallel the plot. So CDEX-1A is here, and CDEX-1B is located here. And this is an interior interior view of the shielding, inside the shielding. So let me explain more about the CDEX-1B. So the CDEX-1B is actually running in two phases. The first phase is from 2014 to 2017. The configuration is as this with the NEI detector cover the germanium. The lifetime is roughly 700 kilo days. And in the run 2, we deliberately remove the NEI detector and replace the detector with some copper shielding. And the run in this data I will show today is roughly 300 days of 300 kilogram days of the data. So both in this experiment, the germanium detector is of a 1 kilo scale mass. Is cooled by cold finger, and NEI detector is used as an active shielding in run 1, but not in the run 2. The detector from 2014 is stable up until now. So the threshold is roughly 160 EV. However, for the annual modulation analysis, we adopt the threshold we start the analysis threshold at 250 EV. The largest uncertainty of this data is based on the bulk surface separation at low energy. I will explain more about this in the next page. So this is a typical germanium detector, a cylinder look like this. So this is a plot. So basically, due to the manufacture of the detector, there's a dead layer, a millimeter thickness of the dead layer without any electric field. So what happens is that if electron hole pair is created in this dead layer, there will be no electric field to drift the charge. So there will be, however, it is possible that this charge will diffuse, and by some chance, it will diffuse inside the active volume, the white one showing here, and then it will drift by the electric field. In this case, this type of event will cause a very slow signal. For a typical bulk event, electron hole pair create inside the bulk region, it will drift immediately by the electric field, and then it will create a very fast signal. The problem is this: because not all the charge at the of this surface event is collected by the electric field, so only partially part of the charge will drift inside the active volume. This will give us a false energy calibration. So what we are trying to do is that to separate these two types of the event, especially in the low energy. And another thing is that since we know that most of the gamma background is actually locate at the surface of the detector. So if we can remove this type of event, actually in the other way, we can remove a lot of the background. So showing here is the signal of the two type of the event. You can see this is a fast and this is a slow surface event. So we can define the time between from the baseline to the full deposit status. So so we call this the rise time, and the y-axis is the rise time of this. And you can see that there are two types of the event, a bug event and the surface event. And in the bug event, you can see since it is energy, it is full energy deposit. So all the KL shell, the peak from the KL shell will show in this region, but not here, because all those energy is quenched, and all those high energy will actually quench to the low energy part, will accumulate in this region. The problem is that we cannot do a simple cut to separate these two events. You can see this surface event actually contaminate the bug down to here. So what we have done is that we can separate these two type of the events statistically by comparing the rise time distribution of different source. For example, here these two are the WIMP candidate spectrum event, and these are the triggered by the anti-Compton detector, which is the main source is a multiple scattering gamma event, and also some gamma carriation source. By comparing the rise time distribution of a different source, actually we can construct, we can find out what is the bug event rise time distribution, and also the rise time distribution of the surface event. The black one is the bug surface bug rise time distribution, and the gray one is the surface rise time distribution. So the bug event count is simply the integration of the black curve. Yeah. So with this, showing here is the three lowest energy bin of the CDEX 1B event. So with this, we can construct the bug count versus time here. So you can see we can separate the event into run 1 and run 2. And bear in mind that is that run 1, run 2 has a very different shielding configuration. So with this, what we are trying to do is that we feed the bin data to a flat background plus a cosine signal with 1 year of the with 1 year period. So first, what we are trying to do is that we would like to see the model independent analysis first. So what we are trying to do is that we feed each bin separately, independently with the previous formula, and then this is the result. The y-axis is the modulation amplitude, the modulation of the cosine signature. So you can see that the black curve is our result. Then this result is consistent with the new hypothesis. And also showing here is the result predicted by Kojon 2013 result, and also by Dharma. And I want to mention something is that this since Dharma and the other three experiment is not with the Dharma is not a germanium detector. So when we draw here, we actually doing some modeling based on the Hero model to do the conversion to show here. But nevertheless, you can see that our result consistent with new hypothesis. And showing here is a model dependence analysis based on the standard Hero model. The red one is based on the annual modulation solely. So based on the modulation signal, we can draw this out. And showing here are all the results with the modulation analysis. So also we are also comparing the same experiment with the same experiment, but with the time integration analysis, showing here the dotted black curve. So, and then we can also look at the phase. We would like to know, we would like to know if there any phase dependence on the results. Showing here is one of the typical plot is a 7.9 GeV with mass. Then in this plot, you can see that between 1 sigma there's no any phase dependence. Yeah. So that, or the other way saying, any phase is consistent with the null hypothesis. And showing here is a broader overview of this statement. Is that the blue one is based on the standard Haro model, phase of the standard Haro model, and this is the 1 sigma best fit region, and you can see it's almost consistent with the 0. And even if we change the Haro model phase to the best fit phase, which is also the maximum deviate from the null hypothesis phase, then we will showing this the black curve here, the black region here, and also it is also consistent with the null consistent with null result between 2 sigma. You can see it here. So, and also this, our result is not consistent with the cojon and also the Dharma. And so the last part is that the other effect we would like to look at is the so-called the Midal effect. When the dark matter hitting a nuclei, usually the whole electron cloud will move together with it, and then it will produce a signal we are looking for. However, there's a small chance that some of the electron or some of the electron will left behind, and then in that case, this electron will occur as a excited state with the final state of the atom. So in that case, this signal will be stronger. The Lecoy energy will be stronger than a typical nuclear Lecoy. Showing here is the Lecoy spectrum of a differential of the electron for this effect. You can see the L shell, the M shell here. So the full Lecoy spectrum will be the combination of all this. And the threshold is here. Let's see. And with this, we can explore the dark matter with a very low mass, below 100 MeV. So you can okay. So why I cannot change? Okay, sorry. So this allows us to probe the exclusion region down to 100 MeV. So this is the time integrate result from this Midal effect showing here, and also comparing is the typical nuclear Lecoy analysis, the dotted black curve here. And for the annual modulation part, showing here is this, the Midal effect here, and compare with the typical nuclear Lecoy analysis showing here. So this allows us to go down to 100 MeV. So the summary. So we have a best modulation high-end result down below 6 GeV, and also the best Midal effect result below 1 GeV, and this is a unique stable low threshold analysis. So the main point is that our data is consistent with null hypothesis, and also other other analysis is on the way. So thank you.
Thank you very much. Other questions or comments for Hau-Bin? I don't see any comments or questions here. Then thank you again. Let me remind everyone that we have the MetaMost chat where we already have some questions discussed. So maybe at least just have a quick look there if there's anything for you. That closes this dark matter session for today at iChap. There are poster sessions today, but not for the dark matter part. So we have our poster session tomorrow. And I hope to see all of you again tomorrow morning, same time. So the early time slot for Europeans. Have a good day and talk to you soon. Bye.
Yeah, there's also some people that have Zoom rooms attached to their talks. So just look up the talks and see if there's 3 or 4 people that can continue chatting in an informal way.
Right, and we also keep this room open just in, I mean, this is open for 1 more hour, so people can just stay here and discuss if there is more discussion needed.
Thank you. See you tomorrow.
Thank you. Bye-bye.
Ciao.